All right. We'll start from here. Let me make the last couple of announcements from here. Okay. First, today we're continuing Chapter 8. We started it on Tuesday. Didn't get very far, but we'll continue in that today. The odds are we're going to take this just about all day today, up until 7:15. At 7:15, if we haven't finished the chapter, we stop the chapter and have the test on Chapter 6. Okay? Hopefully you have your formula and equation sheets ready to go. All right. Then if we still have some of Chapter 8 to do on Tuesday, we'll finish Chapter 8, have the lab on Chapter 8. I will try to have your tests for Chapter 8 ready on Tuesday, and also your final exams ready on Tuesday. Technically, you don't have to take either one of them Tuesday. If you feel ready to, you can, okay, after we finish the lab on Chapter 8. The lab on Chapter 8 is just a paper lab. You'll look up things in the book and fill out the data sheet, okay? But technically, the final exam is scheduled for next Thursday, a week from today. And right now, that's all we got on Thursday. But if you want to take and the final exam consists of two parts, the Chapter 8 test and then the comprehensive part. Chapter 8 part is just like the ones now, take you less than 30 minutes. The comprehensive part probably takes you half that, around 15 minutes. So it's not going to take long to finish that up on Thursday. If you want to try to do that Tuesday and there's time to do it, you certainly are welcome to do so. I'll be here Tuesday, I'll be here Thursday. So it's no skin off my back what day you take it, okay? So if you want extra time to study, take it Thursday. If you want to get out of here, you can take it Tuesday. Or the other option, you can come by anytime Wednesday or Thursday morning and take it. You don't have to come by at 3:15. If you don't want to wait till 15, but you do want to have a little more time to study Chapter 8, then you can come by anytime Wednesday and anytime Thursday before 3:15. At 3:15, the test will be given. Okay? Also, any questions on that? I'll also be returning all your labs and all your tests on Tuesday. First of class on Tuesday. That means anything that's not been turned in by Tuesday at 3:15, too late, baby, it's too late. All right, so get everything into me. That includes your research paper. It's due Tuesday. If you can get it to me today, tomorrow, or Monday, even better, okay? But it's due on Tuesday, okay? Last day of class. And anything time after Tuesday, you start losing points, okay? Have you done the student course evaluations? Yay, nay? How long did it take? 10 minutes at the max, usually. 2 minutes? Okay. I've heard 5 to 10, so yeah, you can get them done. Please do all that they ask for, though, okay? All right, any questions? Chapter 6, Chapter 8, anything? Okay. Now, we'll talk about that later. Since Tuesday's going to be probably our last somewhat late day, it may not be as late as 7:45, do you want to plan to have pizza that day, or would you rather wait and have it on Thursday, or just not mess with it? It's up to you. Tuesday, Thursday, or none? I can't hear it. Tuesday? Is that what I heard? More like supper at the end of class?
Or lunch.
Huh?
Or lunch.
Oh, yeah, he wants lunch because he leaves, right? Okay. On Tuesday, will you have to leave early?
Yeah, I can probably, depending on how early we get out of class, we got to take our final in our other class too.
Oh, you do? Okay.
Depends on how long that takes, I can come back.
Okay. Is that on this campus or the?
Mm-hmm. Yeah. It's just right down the hall.
Okay. All right. So I heard Tuesday. You want it at the beginning of class on Tuesday? 3:15? Sort of a strange time to eat pizza, but it'll be hot then anyway. Okay, want to do that? Okay, I'd say you bring your own non-alcoholic drink. I'll provide the pizza. Does anyone have any dietary restrictions, as in no pork or no beef or no meats or any dietary restriction? Do you have a favorite on pizza kind?
Supreme.
Say again?
Supreme.
Supreme?
Yes.
Okay, I'm probably getting Little Caesars. I don't even know if they have a Supreme.
They do.
Okay. Also, it's close. That's the only reason I'm doing Little Caesars. So Supreme is all right with everybody? What's that? Pepperoni? Anything else? You get to choose for the whole class now. What's that?
I said meat lovers.
Meat lovers? Does Little Caesars have a meat lovers? They do? Okay. Supreme, meat lovers, and pepperoni. Is there anyone you know of in the class that may have can't eat meat or can't eat pork? Every one of those has pork in it. I may get a cheese just in case. Okay? So Supreme, meat lovers, pepperoni, and the class total is 17. How many pizzas you think that's going to be? Think 4 will handle it, or 5?
We don't really have 17 people that show up.
I know, but maybe for the final they might.
Maybe.
Maybe. 4 or 5?
That sounds about right. Yes, sir.
Which?
4 or 5. 5. 5.
Okay, that'll give everybody more than a quarter of a pizza, if you want it.
That should work.
Okay. Okay, 5 pizza, 1 Supreme, 1 meat lovers, 1 pepperoni, 1 cheese, and I'll pick another one unless I hear from somebody. All right, and it's on Screencast-O-Matic, so that'll be Tuesday. And did y'all decide the 3:15 beginning of class? Okay, we'll do it. Okay. No other questions. Let's get started with class. Okay, this is in the text on page 206, right at the beginning, atomic structure discovered. I mentioned Dalton, John Dalton, a British, I'm pretty sure British, I know he was British, but I can't remember if he was Scottish or not. I believe he was just British, scientist, chemist, physicist. He came up with this atomic theory, still called that, even though we know. He went back to good old Democritus and said, all matter is made up of these indivisible atoms. You can't break smaller than an atom. We know now we can. You can break up an atom. That's what an atomic bomb is, okay? But under normal circumstances, atoms are indivisible, okay? An element is made up of all the same kinds of atoms. In iron, all the atoms are iron. In copper, all the atoms are copper. In oxygen, all the atoms are oxygen. In hydrogen, you got it, okay? An element is made up of identical atoms. Different elements have atoms with different masses. And that's where Dalton came up with this. He found out all oxygen atoms weighed the same, all hydrogen atoms weighed the same, all silver atoms weighed the same, all gold atoms, iron atoms, copper atoms, all atoms of the same kind have the same mass. At least pretty close. Different atoms have different masses. Okay? Now, that's elements. Chemical compounds are made up of atoms of different integer ratios. In other words, can anyone think of a compound right off the top? A compound. H2O, water. It's like 2 hydrogens for every 1 oxygen. Always combines in that ratio. 2 to 16. The mass ratio is always 2 to 16. Okay? Because 2 grams of hydrogen, that's 2 hydrogen atoms. 1 atom of oxygen is 16 units. as opposed to 2 units, 1 unit each for hydrogen. Atoms are neither created nor destroyed in chemical reactions. If you start with so many carbons here, you combine them to something else, you got the same carbons at the beginning, at the end. Same hydrogen at the beginning, at the end. Same of everything. You can't destroy or create atoms. They're indivisible, okay? Non-destructible, okay? So the atoms just change configurations. Now the properties change big time. I think we talked about this before, didn't we? Sodium chloride, didn't we mention this before? Sodium is a very soft metal. Okay, you wouldn't even think it was a metal. Very soft. Sort of grayish in color. Explosive. You never find sodium existing in nature by itself. If it comes in contact with any water whatsoever, it explodes. With water, it explodes, okay? It's very reactive. Extraordinarily reactive. That's why all sodium always shows up in other compounds. It never shows up elemental. In a chemistry lab, if you find sodium on the shelf, it's under oil. Why? To keep the water away from it. Even the moisture in the air could make it start exploding. Really a human thing. If you picked it up with your hands, the moisture in your hand, you're going to blister immediately because it's going to try to suck every bit of water out of your blood, out of your finger, out of your sweat, out of everything. Very reactive. Okay? Chlorine. Anyone know what chlorine is? It's what? I can't hear.
Goes in your pool.
Okay, yeah, a chlorine compound goes in the pool. The chlorine itself is a green, poisonous gas. Not a solid, not a liquid, but a gas. Green and very poisonous. Okay? So, sodium, an explosive metal, combining with chlorine, a poisonous gas, what do they make when they join together? Chemically. You've had some today. Sodium chloride, salt that you put on your whatever you cook with it. Okay, everything has salt in it. That's very, very not poisonous, not explosive. It's a stable compound. When you get a chemical compound, the characteristics change completely. Okay? Now, you would think in discovering things about atoms, they would probably start with the big pieces and then find out the smaller ones. Not so. The first part of the atom that was, understand, is indivisible, not completely, but indivisible, that they discovered was the electron. Now, J.J. Thomson in the late 1800s, now his name is spelled the same as William Thomson, who was Lord Kelvin, but I think he came around, J.J. Thomson came later. I don't think there were any kin. Different from Benjamin Thompson, that had a P in it. He was the Count Rumford, who was the British sympathizer who in the Revolutionary War moved back to Britain and made him a count. Okay? This is J.J. Thomson, late 1800s. Okay? He performed cathode ray experiments. Now, does anyone know what that is? A cathode ray is a ray that emits cathodes, okay? And cathodes are positive ions, okay? Here's a picture of the setup, okay? The cathode is here, emitting positive ions going this way. This is your anode, which is emitting negative ions going this way. That leaves the cathode end of it being negatively charged and the anode end being positively charged. It's sort of backward seeming, okay? And he did these cathode ray tube experiments, okay? And what you do is send these things flying along here, and you have, this is in a sealed glass vial, and you have a place where you put a vacuum pump, you try to suck all the air, everything that you can out of that tube, so that the cathode rays go unimpeded. Okay? Now, in doing this, he discovered that really what is moving in there is a negatively charged electron. Now, these are so incredibly tiny that he can't possibly measure them. Okay? In fact, he couldn't even count them. But what he could come up with is their charge to mass ratio. He could tell how much charge was being exchanged and how much mass went in the process of exchanging that, and he came up with a charge to mass ratio. In other words, how much charge passed by a given area, and it actually was going this way, the negative electrons, and how much mass was accumulating on this thing. Very sensitive measurements, but he was able to do it. But he couldn't tell how much each one weighed, just what the charge to mass ratio was. He identified the electron as the fundamental particle that was doing that moving. The positive ions are not moving, generally. It's the electrons that are moving most of the time. Okay. Now, here's sort of how he did it. Here's his cathode over here, and they don't really say what this is. They just have a plus sign on it. Basically what that is the anion but it allows the charged plates to go through. They pick up enough speed, and I think this is just a ring, and it pulls them through, and they keep moving just under their momentum. These are charged plates. Oh my goodness. I think I recognize this guy. Okay. I've seen him somewhere before. Okay. James is here. Glad you're here. Okay, no one else was down at the classroom, were they?
No.
Just the guys working?
I just peeked in there and I heard your voice.
Okay. Were two guys working in there?
I guess I didn't look in far enough, but I didn't see anybody.
Oh, okay.
I didn't see anybody.
Okay. Let me just go
I
check.
looked around the corner.
Huh?
I looked around the corner.
You did? Let me. They may be through. They're not in there, but obviously they're not through. There's nothing in this box, so I can't project from there. All right, so let's continue. So here he has the negative charges, the electrons leaving the cathode plate, going through the anode, but this is open so they can go through. They pick up a certain momentum. Then they go through charge plates. There's a positive charge on one side, negative on the other. It doesn't really matter which is which. Did you finish?
I did all that good. I remembered a lot of it from last year.
Okay. If you don't do it anymore, you through it. Okay. All right. Now, so what happens then is the electrons are attracted to the positive plate, whether it's the one on top or bottom, and they're repelled by the other one, the negative plate, whether it's bottom or top, and then you get now this plate does another thing, okay? In addition to deflecting them, it also screens out some. So now you get a slit of electron coming through, and the positive and negative charges are deflected in opposite directions. The deflection depends on the charge to mass ratio. How much That's it. So you have a detecting screen here, and they determine how much is being deflected. That's how he got the charge to mass ratio. They don't describe it well enough. Now here's the other thing. They've got a magnet here. That produces a magnetic field going this way. Okay? Electron field going this way, and it sort of lines everything up. The moving charge does create a magnetic field. So that's what the magnet is doing for us. It's deflecting in this way. Okay? And that part of the deflection is also part of the story here, because the amount that's being deflected, and if you can register how much is being collected there, you can get the charge to mass ratio. They also do this through momentum, okay, because you know what the momentum of this is. So it's a pretty interesting thing. This slide doesn't tell the story as well as the book does, and even the book, though, leaves some things to be desired, but it gives a little bit more detail than this. J.J. Thomson discovered the electron and determined its charge to mass ratio. Now, folks didn't ask. Okay, let me go back. James, I've said all this before, but in case you don't go back and listen to the first part of the class, we're in Chapter 8 now. We finished Chapter 6 last time. The last 30 minutes today, 7:15 to 7:45, we're having a test on Chapter 6. So if you don't have your formula equation sheet, good to get it together. Okay. Tuesday, next Tuesday, is the last day of class. On that day, I'll be returning all your papers to you, all your labs and all your tests. So anything you don't have done and completed, you need to have turned in to me before class starts on Tuesday. Okay? 3:15 on Tuesday. Okay? Understood? Okay. So get with me, anything that you need by the end of class today, and you can listen to Screencast-O-Matic. You can get with a colleague, whatever, and try to get as much done as possible. Okay? So Tuesday, if we don't finish Chapter 8 today, Tuesday we'll finish Chapter 8 and have the lab on Chapter 8. Lab on Chapter 8 is going to be just a paper lab. You fill out the sheet based on what we've done in the book and in class and asking me questions. Okay? So, then, we also talked about having pizza on Tuesday at 3:15. Okay? And we had an order for supreme, meat lovers, pepperoni, and probably cheese in case anyone can't eat meat. Do you have a preference? Second?
No preference.
No preference, okay.
No pineapple.
No pineapple, okay. Is that on supreme? Okay, good, okay. All right. No, it's not on meat lovers. Okay. So we'll be doing that. Now, here's the deal. If we finish everything on Tuesday and have time to spare after the lab, if you choose to, you can go on and take a test if you want to. If you want to wait and take it on Wednesday, you can, or on Thursday, you can. Thursday morning if you want, or Thursday afternoon at 3:15. Anytime you want to. We'll have the Chapter 8 test and the comprehensive final. Both of them are relatively short. Chapter 8 test you'll probably be able to do in 30 minutes. The comprehensive, more than likely in 15. So they're not going to take, together, they won't take you an hour. So you can either do them Tuesday evening, you can do them anytime Wednesday, you can do them anytime Thursday, or you can do them in class on Thursday afternoon. I'll be here all day Tuesday and all day Thursday. Basically all day Wednesday too, just not till 8 o'clock though. So you'll have your options next week too. All right. Any other questions? Okay. Now, so from J.J. Thomson, we got named the electron, discovered it was carrying most of the charge, the negative charge. He also determined its charge to mass ratio, but could not determine an individual electron's mass. Really, an individual electron's charge either. In came Robert Millikan, probably somewhere within a decade of when J.J. Thomson determined his work, Millikan came up with a really nifty experiment. It's called Millikan's oil drop experiment. And actually, when I was taking a graduate physics course at Georgia Tech, when I went back to school after the Navy, one of the only classes I could sign up for was a physics lab class, which is not particularly my favorite, to do. I wanted to do something more academic, but it's all I could fit in my schedule that I had available and stuff. So I took it. And we did a simulation, a repeat of Millikan's oil drop experiment. Really fascinating. Okay. What you do, you have an atomizer here, a lot like the gals have for perfume, or, if you're trying to just spray a mist water on something, that type of a deal, only have oil in here. Now, oil is neutral. It forms tiny little droplets that you can't even see with the naked eye, okay? And it's sprayed it, and there's a plate here, a charged plate, electrically charged plate, positively charged, and the oil droplets, most of them played out on top, but there's a hole in the middle. A few oil drops happen to fall through the hole. Why do they fall through? Gravity's pulling them through. Gravity pulls everything down. Okay, so these oil drops start falling through this space here. You have a viewing scope. Now, by the way, this is all an enclosed box here. The viewing screen is there, a little telescope-looking thing, microscope type deal. You can look through there, and because of the backlighting and things like this, you can see the oil drops falling. But you have a negatively charged plate down here, positively charged plate here. That means electrons are moving up. Okay? Now, the electrons will attach themselves to these little oil droplets. Not all of them, not some. So some of the oil droplets are falling at a fairly constant rate of speed. Other of the oil drops are moving more slowly. Why would they slow down? Because a negative electron has attached itself to that oil drop, and now it's being pulled up by the positive plate. Other oil drops will slow down even more. Some will actually stop and just sit there. You can look through the scope and see them just sitting there. Others start moving upward. Okay? Now, here's what you do. You figure those that slow down just a little bit have picked up one electron. Those that slow down a little bit more, probably two. At some point, they have almost stopped there. You figure how many that is. Those moving up slowly, maybe one extra, and then another. And by determining the electrostatic force upward, you know that. You can measure that the voltage difference there. You know what that electrostatic force is that's pulling those electrons up. You also know approximately the rate at which the electrons are added to the oil drops, assuming the oil drops are all about the same size, and then you can determine the mass of the electron and how many electrons are on there. So this oil drop experiment, the charge on the droplets are multiples of the electron charge. 1, 2, 3, 5, 10, whatever. Okay. So by detecting those, measuring how much they change the fall, then you can come up with equations that you could determine exactly what the charge on each of those electrons are. Okay? And if you know the charge on the electrons, then you can figure from Thomson's charge to mass ratio, you can get the electron mass. No way you can ever measure the electron mass, but you can measure the charge based on the amount of speed change that you have in these oil drops. Millikan's oil drop experiment. Coupled with what Thomson had come up with, the charge to mass ratio, you can determine the charge on the electron, then you can calculate the mass of the electron. Make sense? All right. So Thomson's result, you don't have to know these numbers, but here they are. The charge to mass ratio for an electron is 1.7584 times 10 to the 11th coulombs per kilogram. Now, kilogram is a whole lot of electrons. I bet you when he did this, he measured it in grams, maybe even milligrams, okay? But the SI unit is coulombs and kilograms. So that's why it's such a huge number, because a kilogram of electrons would be about the mass of this book. You'll never get a mass of that many electrons in one place. It would have such a high charge, you'd be dead, probably. Okay? But that's the number they came out to. Millikan's result was that the charge on an electron was 1.6 times 10 to the minus 19 coulombs. So you see how many, basically on the order of 10 to the 30 coulombs to make 1 kilogram. That's a huge amount of coulombs. Okay? Now, solving for M with these two numbers, then you get, you know what Q is, you get the charge per electron. The mass per electron, 9.11 times 10 to the negative 31 kilogram. Okay, if you change that to grams, that's negative 28 grams. Change it to milligrams, negative 25 milligrams. It is tiny. It's just incredibly, incredibly tiny. No way you'll ever measure that on the scale. But you could calculate it by using these two results. Make sense? Okay. Millikan's oil drop experiment on page 207 on into 208. Okay. I apologize for the low light. Does anyone need at least one light on? The reason it's like this, I'll show you. Whoever wired this, I don't know. You would think this switch would be the front bank of lights, and that switch the back bank. That switch is half the tubes, the middle two tubes in every fixture, and that's the outer two tubes in every fixture.
I think there's a reason behind that, but
is there?
I'm pretty sure.
Okay. There's got to be. Why would
There's a
anyone go
safety
to
reason behind that.
Yeah.
Process.
Okay, come on in. Okay. Can y'all see that well enough with some lights on? Would you rather have it all lights off or just one bank off?
One bank off.
Okay. Is that one any better than that? Any different? Okay, we'll leave it like this then. Okay? Now, let me mark Zach here. Okay. Sorry, we'll go through this again. In case you don't listen to Screencast-O-Matics, but you came today. Tuesday's the last day of class, meaning Tuesday is when your paper is due. I'd love to have the papers before Tuesday. Today would be great. Tomorrow would be great. Monday would be great. Okay? Sooner the better. They're due by Tuesday. Anytime after Tuesday, you're losing points. Okay? Papers are due no later than Tuesday. But I will take them later. You don't want a 0 for the paper, even reduce points. You want some points. Okay. Today we're in chapter 8. I'll hold off and do that one more time.
I'm sitting in the room, Dr. Fowle. I didn't read the note on the outside,
You're kidding me.
Hey, Brian, I didn't even see it.
Okay? I put a note outside, I put a note inside. It's on the board in there too.
I unloaded the stuff and everything, and I said,
Earth to Siegfried, come in please. Okay, never mind. Okay. Was anyone else down there? Were the two guys working down there?
yes, sir, I think it was some guy that realized they went in outside.
Okay, now, James heard my voice and came down. You didn't even hear me, huh?
Dr. Fowle, what's today? Thursday, Tuesday, you couldn't hear you at all.
Yeah.
I thought maybe something. This is
Wishful thinking. Okay, I'm here. Okay. All right, let me go over this again now. Okay, today we're in chapter 8. We picked up, just barely got it started on Tuesday. We're going to get as much covered as we can today. Okay. The odds are we won't quite finish chapter 8 today. Maybe not. We'll see. So therefore, Tuesday, last day of class, we will finish chapter 8, or as far as we're going to go anyway. Tuesday we'll also have, okay, time out on that. Today, after chapter 8, we'll stop by 7:15 because you're going to have the test on chapter 6 from 7:15 to 7:45. Won't take you that long, but I'll allow you that time, okay? So the test on chapter 6 is today. If you don't have your formula and equation sheet, start getting that together, okay? Now, Tuesday, we'll finish as far as we can, probably finish all of chapter 8, and then at the end of that, we'll have the lab on 8. The lab is just a paper lab. I'll pass out the lab sheet. You'll fill in the information and turn it in, okay? Won't take you 2 hours, but I'll allow you at least 2 hours. Now, if you're looking for a plug, I think all the plugs are up front. Is there one back there?
Yes.
Okay, good. Okay. A lot of rooms only have 2, and I saw 2. Oh, yeah, they put this one in because of the projector here. Okay. Yeah, I know you don't want to sit near Siegfried or Nick over there. They're dangerous, but yeah. Yeah. Okay. All right. So Tuesday, we will finish 8. If we don't finish it today, we'll have the we'll have the lab on chapter 8 on Tuesday. Test on chapter 6 today. Okay. Now, technically, your final exam is Thursday, a week from today. Final exam consists of chapter 8 test and the comprehensive test. Chapter 8 test won't take you more than 30 minutes. Comprehensive won't take you that long. So in less than an hour, you'll be through. Okay, so what we talked about, I said y'all want to have pizza one day. And most people said, let's do it Tuesday. I was thinking you might want to do it later, but they said let's have it early. So we'll start with 3:15, we'll have pizza. Any dietary restrictions? I've had a request for supreme, meat lovers, pepperoni, and I figured we ought to get a cheese in case anyone can't eat meat. Okay? Okay, that's 4 pizza. Y'all wanted 5. I'll get one. If anyone has a request for something else, I'll get it. Otherwise, I'll get double on one of them. Don't worry about it. I'll do the pizza. If you want something to drink, non-alcoholic, bring your own. Okay? No, I said non-alcoholic. Your ears are selective hearing. Okay. Okay. I'll bring all the alcohol that comes in the room. I'll put it that way. Okay. Okay. All right. But if you want to bring anything, but you can't bring anything alcoholic. Okay. Okay. And then now, here's the other deal. If you want to take the test early, once we finish everything on Tuesday, if you want to take the test early, either Tuesday evening, anytime Wednesday, Thursday morning, or regular class time Thursday afternoon, I'll give it to you anytime you want to take it. You could take the chapter 8 test first, and then wait a day or two and take the comprehensive. You can take them both, same day. I don't care. You can wait and take them both on Thursday. I'll be here all day Tuesday. I'll be here all day Thursday until 8 o'clock both days, and I'll be here till probably 4:45, 5:15 or something like that on Wednesday. So you have your choice. I'll have them ready. Anytime you want to take them, you can take them after we finish the lab on Tuesday. Okay? Wednesday, Thursday, whenever. So that way, if you don't have to stay around, if you got everything else done, you don't have to stay around till late Thursday night to finish. Okay. The other thing, have you done your student course evaluations? Yes, very good. If you haven't, please do those. All right, we talked about J.J. Thomson. He discovered the electron. He determined the electron's charge to mass ratio, but he couldn't determine the charge or the mass. until Millikan's oil drop experiment came along, and then they could determine the charge, and from that they could determine the mass. Okay? Now, early models of the atom were Dalton's, the atoms are indivisible. Then we had Thomson and Millikan experiments, determined the electron mass to be incredibly tiny, no measurable volume, incredibly tiny mass. So what is the nature of the atom's positive charge? Well, Thomson, same Thomson here, he came up with a concept, an idea, a model called the plum pudding. Okay? He thought the positive charge was in the pudding, scattered throughout the pudding, and the plums were just scattered somewhere in the pudding. And you can think of this as, my wife does a bread pudding and it has raisins in it. Same type deal, okay? The negative charge would be the raisins or the plums, and the dough, the rest of it would be the positive charge. That the electrons were embedded in a blob of positive charged matter like raisins in a plum pudding. I thought there were plums in the plum pudding, but I guess it's raisins, okay? So that was Thomson's model. Think it worked? Well, here came Ernest Rutherford. What was that? 2 years after Millikan? No, 1 year after Millikan, about 1 year after Millikan. And he said, okay, let's see what we got here. And what we did, now we talked about electrons being charges, but there's another thing that carries a charge. Have you ever heard of an alpha particle? An alpha particle is we know today as being the nucleus of a helium atom. Now, they didn't know this back then, okay? All he knew, it was a +2 charge. He could separate it, he could do it, and he could send these out there. These were very small +2 charges. They're called alpha particles. We know today there are 2 protons, 2 neutrons in the nucleus, okay? The electrons have been stripped off. Now, what he did, he fired these alpha particles, 2 positive charged particles, into a gold foil. Now, gold, in some ways, is sort of like aluminum. Aluminum, you've used aluminum foil, right? You can have that stuff really thin, right? Gold, you can make even thinner. Gold is a soft metal, and you can roll it out and extrude it out until it's almost translucent to look through. You can't see through it, but you can see light on the other side. Really thin gold foil. The deal is you only have a few molecular layers there, atomic layers. So he had this very thin gold foil, and he was going to fire these alpha particles at it. Now, if gold is made up of plum pudding with a blob of positive charge with the electrons stuck in the plums, the raisins in the plum pudding, then basically most of the alpha particles are going to get absorbed or repelled by that blob of plum pudding, right? Okay. But guess what? Most of those alpha particles pass right through with no deflection at all. Wait a minute. Obviously, it's not a blob of positive charge. If it were, they would have been deflected pretty major. Most of them backwards because they're positive charge. A few of them, very few, scattered at really large angles, though. Okay, really large angles. What's the conclusion? That the atom has the positive charge in there, but it must be extraordinarily small. Okay? But extraordinarily massive. Because remember the electron? The mass was almost nothing. I mean, really, really tiny. Okay? So most of the mass was in the nucleus, but the nucleus wasn't a plum pudding. The nucleus was some tiny, tiny little, but very massive particle, okay, in the middle. Later they determined those positive charges in that nucleus were protons. Now these few that were scattered at large angles, those were those positively charged alpha particles that bounced off of were repelled by those really concentrated nuclei. Okay? And that's when they discovered, no, the electrons really sit out in a cloud around those nuclei, not stuck in the middle of the nuclei, but in a cloud around the nuclei. So guess what? Most of that gold, which is a very dense material, most of the gold is empty space. It's got a very dense nucleus. That's where all the mass is. And then a cloud of electrons around it, almost no mass and almost no volume. So most of that is just empty space around that nucleus where the electrons fill it up. That's why most of them passed with no deflection at all, but the few that were scattered, really large angles because they were really pushed backwards. Now, much later, 25 years later, James Chadwick also determined, in addition to the protons in that nucleus, there's also neutral neutrons. That's why they call them neutrons. They're neutral. N-E-U-T-R. That's the same in both. Neutral neutrons. Those were also residing in the nucleus. Now, all right, here's Philip. Did you sit down in the classroom long?
No,
Oh. Okay. We won't tell you we did. Okay. Just kidding. Okay. Okay. Just kidding. Okay. Let me, got to give it to you a little bit. Okay. Let me, sorry to do this over and over, but maybe everyone will hear it and remember it then. Today we're in chapter 8, continuing chapter 8. We will go either until we finish the chapter or reach 7:15:1. Okay? At that time we'll stop and you'll have the test on chapter 6. Chapter 6 test. We finished chapter 6 last time. We finished all 3 labs on chapter 6, and that test will be at 7:15 tonight. Unless we finish the chapter early, then we'll have the test early. All right. Tuesday of next week is our last day of class. A couple important things about that. Your paper is due by Tuesday. I'd love to have it today. I'd love to have it tomorrow. I'd love to have it Monday, or I'll take it on Tuesday. Anytime after Tuesday, you start losing points. Okay? So get your papers in sooner rather than later. Okay. Tuesday, I'm almost certain we'll finish the chapter by Tuesday, sometime Tuesday. Once we finish the chapter, then we'll have the lab on chapter 8. The chapter 8 lab is just a paper lab. You'll have your books open, you'll have your notes from class, your PowerPoints, whatever, and you will fill in the sheets on the lab. Okay, it's just fill in the one-page data sheet. Okay? Hopefully get those finished and turn them in to me, and I'll do that. Get them graded. Now, technically, your final exam is scheduled for Thursday. Final exam will consist of a Chapter 8 test, about like your other tests have been, maybe a half hour, you'll be able to finish it. And then a comprehensive final, which is going to be even easier and shorter, and you can finish that probably in 15 minutes. Okay? So, that's all that's scheduled for Thursday. Now, let's back up to Tuesday. Because a lot of people might be thinking that might be their last day here. They said, let's have pizza on Tuesday. Do you have any dietary restrictions? Okay, we've had a request for meat lovers, supreme, pepperoni, and I figure in case anyone can't or doesn't want to eat meat, I'll get a cheese. Okay? So those are the 4 requests. If you have any other requests, let me know. I'm going to get up to 5 pizzas. If I don't get another request, I'll get 2 cheeses or 2 pepperonis or something like that. Okay? All right. That'll be Tuesday at 3:15. Okay? So now I'll provide the pizza. If you want any non-alcoholic, Zach, drinks, you can bring those yourself. Okay? I will not be providing drink. There is a water fountain just right next door to us here. Okay. Now, the other part of that puzzle is if you don't want to wait until Thursday afternoon to take your final, if that's the last thing you've got and you don't want to sit around another day or two just to take this final, which is going to be done in 45 minutes to an hour, if you want to take it after we finish the finish the chapter and finish the lab on Tuesday, you can take it then. If you want to wait till Wednesday morning, you can come and see me Wednesday morning and take it then. Wednesday afternoon, fine. Thursday morning, fine. Or you can wait till Thursday afternoon. I'll be here all day Tuesday, all day Thursday until 8 o'clock each day. And on Wednesday, I'll probably be here 4 or 5 o'clock, something like that. So you got any time you can come take your test. Okay? Or you can wait till Thursday afternoon when it's scheduled. I'll be here. Now, what you can't do, I forgot to say this earlier, you can't wait till Friday of next week and say, can I take it Friday? The answer to that one is no. The reason? I'm not going to be here. I'm going to be heading to New Orleans. I've got a meeting down there Friday evening and Saturday, coming back Sunday. So I will not be on either campus on Friday. So don't figure you can wait till Friday to take it. Okay. So, but you can take it Tuesday, Wednesday, or Thursday. Tuesday after lab, anytime Wednesday, anytime Thursday. Okay? Pizza at 3:15 on Tuesday. All right. Any questions? All right. So we were talking about the nucleus, how Ernest Rutherford discovered that the nucleus is comprised of a tiny little, very, very massive body in the middle, and then a huge cloud of electrons floating around it. So here was an example of Rutherford's study. Okay? Here he had his radioactive source, alpha source. That's where it's coming from. They didn't really strip the electrons off the alpha. They just knew they were positively charged. Radioactive. Dangerous stuff. Not super dangerous, but dangerous. Here is this very thin layer of gold foil there. The alpha particles hit that, and most of them don't get deflected. They go right through and hit right here. Okay? This is your detecting string. Most of them, just vast majority, go right through the foil. Don't get deflected by anything. A few get deflected a little bit, but most that do get deflected are back this way. Very, very sharp deflections. Okay? What that means is most of that gold, and gold is a very dense atom, most of that, they go right through without hitting anything. Just rarely they hit the nucleus and bounce back at some angle. They may get veered off like that because the alpha particles are positively charged, the nucleus is positively charged. And most of them go right through without any deflection at all. So this is how he added to what he understood. Here's the sort of the visual of what it is. So that's a very, very, very thin gold foil there. It only has a certain number of molecules in it, okay? Probably more than 3 deep, okay? More like 5 or 10. And they are sort of scattered throughout there. But most of the alpha particles that come through, if they don't actually hit a nucleus, they go straight through, like that one and that one and that one. Most of them go straight through, but occasionally you'll have one that comes up and glances off the edge of one, or gets deflected back this way, or even that way, or that way. Very sharp deflections, but they have to actually hit a nucleus. So most of everything is nothing. But there's nothing in there to block those alpha particles, except very rarely do they get deflected. That showed that the nucleus was extraordinarily small and therefore very, very dense. All right. Now, the top of page 208 is a case study. named after an English physicist, William Crookes. By the way, if you haven't chosen a paper topic yet, we've just today talked about J.J. Thomson, Milligan, Robert Milligan, James Chadwick, Ernest Rutherford, and now here's English physicist William Crookes. Now you don't need to talk about it. We talked about Millikan oil drop experiment. We talked about the Rutherford experiment. We talked about the J.J. Thomson's experiment. There's tons of things we just mentioned today. The nucleus, the proton, the neutron. Everyone could get a different topic just on today's lecture, okay? But if you want to, look here. Here's William Crookes, okay? He came up with this tube, okay? Early study of electricity, and I believe this is what we now call the cathode ray tube. I'm not sure if it's the same thing, but it was pretty similar. Then look down a little bit later. These names were invented by Michael Faraday. Now, I don't know if y'all know who Michael Faraday is. Another great, I think, British physicist. He did a lot of work with inductance, largely, okay? Does anyone know what a capacitor is? Say again? Okay, yeah, the capacitors everywhere. Capacitors in these light fixtures. The ballast up there, that's basically a big capacitor. Okay, Tiffany's here. My goodness, we're going to come in one at a time, aren't we, today? I think I'll wait till a few more people come in until I go through my whole spiel again. Okay, y'all have heard it so many times. But before the end of the day, ask me to go through my spiel, telling you how we're going to finish the term. Okay. All right. And certainly before you, yeah. Okay. So the unit of capacitance is a farad. Microfarad, farad, named after Michael Faraday. Okay. So there's another name here. All right, so that little blurb there, discovery of the electron, that can't be a source for your paper, but it can give you ideas for your paper. The book cannot be your source. On the next page, another case study, the oil drop experiment, mentions J.J. Thomson again, but we know this was done by Millikan, and that's the first part is based on J.J. Thomson, second part, Robert Millikan, okay? And there's some questions on each of those. This can't be a source for your paper, but it can be the source of ideas for your paper. You go out and find your sources somewhere else. Okay. Now, there's not a subtopic in the book that's named the nuclear atom, but this is under the nucleus, okay? So we'll see some of this coming up. The nuclear atom, okay? Every element has a unique atomic number. What is that atomic number? It's the number of protons in that nucleus. If you have a hydrogen atom, you have one proton. If you have one proton, that's a hydrogen atom. If you have two protons, that's a helium atom. 3 protons, that's a lithium atom. 4 protons, that's a beryllium atom, okay? It goes on and on and on. Every element has unique number of protons. That's the atomic number. It's a whole number. It's no decimal. 15. Look up in the periodic table for element number 15, and you see that is phosphorus. If you have 15 protons in a nucleus, it's got to be phosphorus. Okay. Now, the elements are distinguished by this atomic number. the number of protons. And guess what? Atoms don't go around gaining or losing protons, ever. How they become charged is gain or lose electrons. They never gain or lose protons. So they say that. Now, when this slide was done, they said 113 elements were identified. If you look at your periodic table, that is a couple pages over in this table chapter, or easily to find at the end of the big book, if you got a big book, if you go down to 113, that only covers through unanimity, okay? That's just a made-up name. The one right before that is Copernicum, okay? Named after Copernicus, okay? The next one is Flavoronium or something like that. That was named after somebody. That 113, they know it's there somewhere, but no one at this time had discovered it. Oh, by the way, there's another, Livermorium, okay? So there are a few that have been named, but guess what? This was more recent than the slide, okay? Basically around 115, something like that, have been identified. But most of those bigger numbers, even when they've identified them, they are such short-lived radioactive atoms, they last for a fraction of a second and are gone. They lose an alpha particle or beta particle or gamma radiation, and they no longer are there. So even those high numbers, they're not there for very long. So the number of protons is equal to the number of electrons in a neutral atom. Because guess what? If it's neutrally charged, it's got to have the same number of electrons as it did protons. If it's not neutrally charged, is that an atom? What is it called? There is a car named this. I can't think which make it is. Isn't there a model called an ion? I-O-N? I'm guessing. I think I've seen that somewhere, but maybe not. I know there's a cyan, okay, but I thought there was an ion too. Okay, if it's not neutrally charged, it's an ion. That means there's either extra electrons or a deficit of electrons, okay? But if it's not an ion, if it's a neutral atom, the number of electrons must equal the number of protons. Now, if you also look in that table, you'll see another number. You see the whole number, 1, 2, 3, 4, 5, up to, actually this table lists 118, but not all of those are named. Okay? You'll see another number that's always a decimal number. Hydrogen is 1.008. Lithium is 6.941. Manganese is 54.94. You know, they all have some decimal number. Where are those decimals coming from? Well, here's what the deal is. The isotope has the same number of protons as the other isotopes of that element have, but it could have a different number of neutrons. Because guess what? Neutrons have a neutral charge. You can gain or lose neutrons and you stay the same material. What happens if you gain or lose protons? You don't gain or lose protons. You can't. Gain or lose neutrons, you become a different isotope. What happens if you gain or lose electrons? You become an ion, charged. You're no longer neutral. Okay? So the isotopes always, if you're the same material, you don't change the number of protons, but you could have different numbers of neutrons. And here is the classic example of this. Hydrogen has 3 isotopes. Most hydrogen, the vast majority of hydrogen, something like 999 out of 1,000, maybe that's not quite right, but close to it. I'm going to say 992 out of 1,000 is going to be 1 proton, no neutrons, and 1 electron. That's called hydrogen 1. That's most of the hydrogen you ever will find is this hydrogen. Okay, now what does this nomenclature mean? The lower one down here is the atomic number. One proton, that's hydrogen. The upper number is the atomic mass. One proton's all that's in there, so it's one. Okay? But hydrogen 2 has a name called deuterium, meaning two, duo, double, deuterium. It has one proton and one neutron, so therefore it has an atomic mass, approximately 2. Atomic number of 1 is hydrogen, but it's twice as heavy as this is. Twice as heavy. Okay? That's deuterium. So your mass number's up here, atomic number down there. Tritium, really heavy for hydrogen, still the lightest material there. 1 proton, 2 neutrons to give you a total atomic mass of 3. Really heavy. Now, most of your atomic energy plants, okay? I grew up, most of the time growing up in Burke County, Georgia. And in Burke County, Georgia, right over on the Savannah River, is Shell Bluff is a community. And over there, Georgia Power and others have built a plant there called Plant Vogtle. It's a lot like one of the nuclear power plants that Alabama Power owns somewhere around here. Does anyone know where that is? I don't think Wilsonville is. I think that's coal power, isn't it? But there's a plant somewhere in the area here that's nuclear power plant. Maybe not real close, but somewhere around. I can't think. Does anyone know? But in Georgia, Plant Vogtle is a nuclear power plant. Okay? They're on the Savannah River. Just about every nuclear power plant you'll ever find is going to be on a river, except a few like in Japan. They put them right on the beach, right? Yeah, that's it. They're by water. Now, there's 2 major reasons for that. One is nuclear power produces an awful lot of heat. So they got to dissipate the heat somehow, and they use water, because water, if you remember from chapter 4, has the highest specific heat of any material around, naturally occurring material. Helium's a little bit higher, but that's not very prevalent. Water's all over the place. So water has a very high specific heat. So most of that water that they use is for cooling. They cool it, and then they put it back in the river or back in the ocean. So that got it. But the other reason they're around water, when they're pulling that water out, they're centrifuging. And in those rare cases that they come up with water that has at least one of the hydrogens being deuterium or tritium, then they call that heavy water, because it has extra. Because you think water has oxygen, which is 16 atomic mass, and 2 hydrogens, that makes it 18. If one of those is a deuterium, that makes it 19. If both of them are deuterium, it makes it 20. If one of them's tritium, it makes it 19. And if one of them's, it's 20. And if 2 of them are tritium, which is very rare, it would make it 22. So it's heavier water than the other water is. So they centrifuge it to get the heavy water. Why do they do that? These extra neutrons here are the things they use to control the nuclear reaction. Remember you probably didn't watch the science fiction things when they push the tubes in to slow down a reaction or pull them out to speed up a reaction. What those were in the tubes were neutron sources. Heavy water was one. And the extra neutrons there slow down the nuclear reactions to keep it from overloading. So, because tritium is 3 times as dense as regular hydrogen. It's still hydrogen, but it has 3 times the mass of what this one does. So you can really do a lot with it. Water is very prevalent, and they separate out that heavy water so they can use it to control their reactions. The second use for that, the reason that they're near water. All right. Now, this slide is a lot like the previous slide. It just says it in a slightly different way. the mass number that you see in your periodic table is the number of protons plus the number of neutrons. Wait, shouldn't that be a whole number? And most of those mass numbers have decimals in them. Well, there's two reasons for that. They have to sort of normalize it, and they make an atomic mass unit, and that's called U, sometimes just unit. But it's really, in the old days, it was AMU for atomic mass unit, to be 1/12 of the carbon-12 isotope mass, okay? Just to get a normalized number, okay? And then anything more than that, or less than that, that gives you your decimal, okay? So what's the atomic weight? Well, the mass number is protons plus neutrons. Wouldn't that be the same as the weight? No, not necessarily. Here's why. It's the atomic mass of each element averaged over those naturally occurring isotopes. So that's why hydrogen is not 1. It's 1.008 because you have a little bit of deuterium and very little tritium. And that's why I said on average it's only 1 out of, or 992 out of 1,000 would be pure hydrogen, mass number 1, and some of the others of them would be deuterium or tritium. Okay? So that's what we do, average over the naturally occurring isotopes. So anytime you see those fractional numbers there, I'll just pick out a few of them. Hydrogen, most of the hydrogen is 1. Helium, most of the helium is 4. You have a few that are 5, but not very many. About 3 out of 1,000. Okay? Lithium, most of them are 7, but you have a few that are only 6. So therefore the average is 6.941. So you see they can either be an extra neutron or a deficit of neutrons. That makes your different isotopes. And that's why the atomic weight is a number that's a decimal number. Very few of them will be right on the nose. In fact, I don't think any of them are. They all have some sort of isotopes. And that's why the atomic weight is always a decimal number. Round it to the nearest one and you get most of the prevalent number of neutrons would be. You can calculate that. Okay? Here's the same slide we had before. Why they show it twice, I don't know. But this shows atomic mass, atomic number, number of protons, atomic mass. That's protons plus neutrons. How many neutrons does this hydrogen have? None.
0.
Because this is all a proton. Okay. Okay. How many neutrons does this one have? 1. This one. 2. You subtract this from that and you get the number of neutrons. Because this is the mass of the nucleus, this is the number of protons, so the difference of those is the number of neutrons. Make sense? Okay. So, here's how we do. Let's take nitrogen, for instance. If you go to your periodic table, you see that nitrogen is, what is its atomic number? Yeah, N. First, okay. Say again? Nitrogen, what's its atomic number? 7. What does that tell you? How many? Say again? The atomic number gives you how many? I just said it about 15 times. Protons, exactly. Now what's nitrogen's atomic mass? 14. Okay, now the 0.01 we'll get to in just a minute. It rounds to 14. So on average, how many neutrons does each nitrogen atom or nucleus have? Subtract the 7 from 14. 7. But a few of them have 8, like 1 in every 100 or so. Okay? So here's what you have. This is nitrogen with 7 protons. All nitrogen has 7 protons. 14 masses in the nucleus, so that means 7 of those are neutrons. But there is also a nitrogen 15 that has, of course, 7 protons, because all nitrogen has 7 protons, but it has 8 neutrons. So this is, natural abundance of this is 99.63% is nitrogen 14, and 0.37%, that's less than 0.5%, contains the extra neutron. So what you do is multiply your 0.9963, if you make it a decimal number, 0.9963 times 14, 0.00307, that's this mass, and multiply the 0.0037 times the 15.0001 atomic units, and that's how you get the 14.00. Your book says 7, doesn't it? Or does it just do it to 1? 14.01. So it's rounded this 6 to 1, 14.01. Okay? That's why you have the decimal there. Because you have some 14, most of it's 14, occasionally, like 3 in every, or maybe 4 in every 1,000 will be an extra neutron. So it's going to contribute a little bit. So that's why you have the increase there. Does that kind of make sense? Okay. Now, let's then go to what we call, by the way, discovery of the nucleus. We mentioned Democritus earlier. Then J.J. Thomson discovered electrons. And so there's more here, just another case study, well worth your read. There's a table here, table 8.1. They don't show it in the slide set, but it shows some of the early elements here. It only shows regular hydrogen and deuterium. It doesn't show tritium. Okay? It shows 1 beryllium. Can you tell me, looking at the beryllium they have listed there, how many neutrons beryllium has? 5. You're absolutely right. Okay? Oxygen. How many isotopes of oxygen does it list? No, oxygen. How many isotopes of oxygen? How many do they? Oh, there's Lacey. No, you're in here. There you are. Okay. So we have 2 people who haven't heard the spiel. Okay. Was anyone else? Did you go by the classroom? Did you go by the classroom? Oh, you didn't. How did you know we were here? You heard. Okay. It must have been Zach talking too much. Okay, that must have been what it was. What's that? Oh, I see. Okay, good. Thank you. Okay. They were putting up the projector. I just wondered if anyone else was sitting in the classroom. No. Sorry. You don't know. You didn't check. Okay. So you don't know if the guys are still in there working. Okay. Well, we'll find out. Okay. So 2 people have come in since I gave my spiel. I'm going to wait and see if anyone else comes in. Maybe wait until just before test time, but certainly before anyone else leaves. We're looking at oxygen on the table on page 210 or whatever it is, table 8.1. In my book, sort of a greenish table. How many isotopes of oxygen are listed there? 3. Okay. The most common one, 99.759, how many neutrons would it have? 8. The next most common look at your table in your book. Actually, the next most common is 0.2, not 0.037. That has 10. You see it? And then the third one is the one with 9. Okay? Now, the surprising thing with that is the atomic weight is less than 16, but all the isotopes are more than 16. Well, the reason for that, remember, it's all based on carbon-12. Carbon-12 is just a little bit heavier than oxygen. I don't know why, but it is. Okay? How many isotopes does neon have? 3. What's the most common? How many neutrons? 10. The next most common? 12. And the third most common? 11. Got it. Okay. They show that beryllium, fluorine, and aluminum have basically 100% are all the same isotope. But yet it's not exactly that number either. Close to it. Okay. Then there's another concept applied, and that's atomic parts. Okay? And that's what we've been doing. You look at the atomic mass, you look at the atomic number. The difference of those two is the number of neutrons. What does the atomic number tell you? How many what? Protons, exactly. And in a neutral atom, that's also how many? Electrons you have, because if it's neutral, the same number of electrons as protons, because they're charged. All right, so now we're moving to 8.2, classical atoms. Okay? Actually, this is a little before 8.2. This is the preliminary part. Okay? Predictions of the classical theory said that the electrons orbit the nucleus. Okay? That makes sense. Nucleus is here, the electrons go around it. Sort of like the planets around the sun. So planets around the sun all go in pretty much the same plane around the atom. They go all over the place around it. Okay? But the path of the electron is curved, right? It's got to stay around there. So if it's curved, it must be accelerating. If it's accelerating, that means accelerated charges have to radiate electromagnetic radiation. If they're irradiating a thing, they're losing energy. If they're losing energy, they're going down and crashing into the nucleus. Guess what? That's not happening. Wait a minute. The conclusion for this, atoms can't exist. Okay. Well, obviously atoms do exist. There must be something wrong with our model here. Okay? Experimentally, atoms do exist. A new theory is needed. Anyone want to guess what that new theory was? Y'all, some of you are auto mechanics. Some physicists are quantum mechanics. Okay? It's the quantum theory. Okay? And boy, have we ever got enough names here. Okay? Max Planck. Way back around 1900, this was actually before Rutherford did his experiment. Millikan did his experiment. So back then, Max Planck introduced the concept of quantized energy. Okay? And here's what he said. A photon, if you watch much science fiction, you have photon guns, stuff. Well, that's science fiction. But a photon, the energy of a photon is proportional to the frequency of that photon. Okay? The constant proportionality is a constant, and that's called Planck's constant. Okay? And that happens to be 6.63 times 10 to the negative 34 joules second. Not joules per second, joules second. Why is that true? Because this is in joules, energy is in joules, frequency is in per second, cycles per second, something like that. per second. So this has to have a unit of joule for here, and second cancel out the per second there. So it's a joule second, but an extremely tiny number, terribly tiny number. Okay. Now, just a little bit of Max Planck, not much, but a little bit. Several years ago, I believe it was 2008, 2009, we hosted an Italian kid, lived with us for a year. His parents were good friends of ours. His dad had graduated from UAB in public health, the same class my wife did. They got the PhDs in public health. And they were really close, and Fabio and Rita had been married just a few months after we were. We didn't know this at the time. So we did a lot of things together. We enjoyed them a lot. They were a lot of fun. And after Fabio graduated, and Karen too at the same time, Fabio got a job up in Boston and moved up there, and that's where their first child was born, a son. His name was Giacomo, meaning James. Okay? So he was born in the U.S., so that made him a U.S. citizen, even though both his parents were Italian, but that's the rules. So anyway, they worked there for about a year, and Fabio's parents were just on him like crazy to move back home to take care of them, and stuff. So he got a job back in Italy, so they moved back. Their two daughters were born in Italy. But then Giacomo was really a bright kid, and his parents were sort of hoping that he would have the option of either coming to the U.S. to study, go to college, or to go in Italy. He always could go to Italy, but they wanted to have the option of coming to the U.S. Well, they knew our systems were different, so they thought it might give him a little bit of an edge if he could graduate from a U.S. high school. So we went over to visit them. Karen had professional meetings in Italy, and I got to go with her because it was just the week of one of our breaks. So I got to go with her, and we went up to Trieste to visit with them. And we met Giacomo. We had met him earlier when he was in junior high, but he was now somewhere in high school, sophomore year, something like that. And we got along really well. And that's where Fabio got the idea then. He had already been trying to think of a way to get Giacomo over here so he could do his senior year in the U.S. He said he got along well with Charles and Karen. He asked us if we'd do it. We said, sure. So Giacomo came over and went to high school near where we lived. And so he got his high school diploma. Well, Italy required a fifth year of high school. So he went back and graduated from high school in Italy the next year, okay? So he did a high school diploma here and there. So he could go anywhere he wanted to. Well, that year he came back, had a full ride from University of North Carolina. They would have paid for everything. He said, go for it, good school, But he got accepted at Harvard and wanted to go to Harvard, So he went to Harvard. Boo hiss. Well, they didn't pay much on it, His parents had to sell their house basically to afford to go to Harvard and move into an apartment. So not a good deal. But anyway, he then got his degree here, went back and did some study back in France, and he's now working on his PhD. Okay. I'll come back to that in a minute. We have German friends in Birmingham. Long story there, but actually the guy, Olaf, is from Munich. His wife, Miriam's from Wiesbaden, another part of Germany. But they went to graduate school together. But we have hosted Olaf's parents when they came over, when their first grandchild was, and only grandchild at the time, was baptized, here. So we had them at our house. So we've gotten to be good friends with the parents too. They live in Munich. So we went over and visited them that same time, or some later time. Karen had meetings in Germany, so I got to go there. And we visited with them. And Mr. Cooch, he's retired, but he had worked at the Max Planck Institute. And when we stayed with them, just 2 train ride stations up the road, up the track, was Max Planck Institute. And he took us around there and showed us the Max Planck Institute. Very famous German scientist. Back to Giacomo, he's now getting his PhD the Max Planck Institute in Germany, just a couple of blocks from where our German friends live. You know, it's a strange small world, okay? But anyway, Max Planck introduced this. And by the way, Max Planck Institutes are all over Europe, not just in Munich, but several places. A few years later, this strange new character from the U.S., though he was originally German, named Einstein, okay? Albert Einstein in 1905 added to what Planck had said, this idea of quantized energy, and said that light was made up of quantized photons of energy. And in fact, that's exactly what's happening inside these tubes. Okay? What you got in there, someone mentioned the capacitors. I mentioned it, but then I think it was Nick mentioned the capacitors. Well, capacitors are in here, building up a lot of charge. They build up charge, and then the electrons fly down the tubes here. Actually, it's ions, mercury vapor ions, fly up and down the tubes there, okay, at very high rates of speed, carrying with it energy. The inside of those tubes is a white phosphorescent material. You've seen it probably if you've ever broken one of the tubes, that white powder. Well, that phosphorescent material, when high energy ion goes by, it'll jump up. One electron will jump up an energy level. We're getting a little ahead of ourselves here. When the ion passes, then there's nothing to keep it up there, and it falls back down again. When it falls back down, it gives off a photon of energy, of light energy. That's why this produces white light, because those electrons are falling back down, producing light. They got the energy from the ions passing through. When they fell back down, they gave up a quantized photon of light. Einstein came up with the theory that said that, long before they had fluorescent tubes. Okay. Higher frequency photons means more energetic photons. So higher frequency, you have more energy. Okay? That's why gamma radiation will kill you, because it's very ultra high frequency. The energy is enough to destroy tissue, to kill tissue. That's why you go out in the sun and get too much ultraviolet radiation. You get skin cancers, you get cataract. It destroys tissue. It's higher frequency, higher energy radiation. Okay? That's why this guy or gal, whoever it is in there, has some protection on what they're doing. They never describe what the picture is, but it's a pretty picture. Okay. Now, that's the quantum concept. Let's back up here. Nope. Let's do it here. Here we have, okay, they got you. Okay. Who was it just left? That's who they got for leaving class. Okay, never mind. Okay. Here's example 8.1. What is the energy of a photon of red light when red light has a frequency for red light is equal to 4.60 times 10 to the 14 hertz. Why in the world do we have a quantity that has a symbol Hz? Because we already had a unit that was H. That's a Henry. Henrys measure inductance, I think. Some of you electrical people. Is inductance measured in Henrys? I believe it is. Okay, so therefore this guy, oh boy, I can't think of his first name now, Heinrich Hertz, another German, was the one that first started talking about, or early talked about frequency, and they named the unit after him, Hertz. And really what a Hertz is a per second. Cycles per second, whatever per second. A per second is a hertz. So this is, the actual unit here is second to the minus 1, or 1 over second, whichever way you want to say it. I like 1 over second better, but second minus 1 is a little easier to write. Okay. So that's the energy of that. I mean, that's the frequency. Well, what did we just say the energy was? Boy, this is a squeaky school, isn't it? Okay. Energy is equal to, okay, HF, right? We just had that, okay? It was on the previous slide. Oh, there it is, at the top of page 211 or whatever closer to it, equation 8.1, E is equal to HF, where the H is Planck's constant, named after Max Planck, 6.63 times 10 to the negative 34 joule seconds. Multiply that by 4.60 times 10 to the 14th. How did I get a 4 there? I knew that wasn't right. 14th hertz, and hertz is a per second, right? Notice here the second up here cancels the per second there. And if any of you have a calculator that can do this, 6.63 EE or EXP negative 34 times 4.6 EE or EXP 14, and what do you get? So it's like 24, 25, 26, something around in there. No, actually 30, right? Yeah. 3 point, anyone get it? 05 times 10 to the, now you see that gave you 24, which actually because of those big decimals goes up to 30. And this would be 10 to the minus 20, but you went one more up, so it's minus 19. And the only unit you got left is joule, which is a great unit for energy. Okay, you did something wrong. Okay, let me come watch you plug it in. Okay, yeah, 3.049. Yeah, that's it. 3.049, which they rounded 3.05. Why did they round to 3.05? You only had 3 digits here. You only had 3 digits here. So you can't have 4 digits here, round to the nearest 3. So 3.05 times 10 to the minus 19 joule, which is a tiny, 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 tiny amount of energy, but that's one quantum of energy. Okay? A photon of energy. Okay, let's do 8.2. What is the energy of a photon of violet light? Okay, with a frequency F for violet. Now, red is at the low energy end of the spectrum. Violet is at the high energy end of the visible spectrum. With a frequency of 7.30 times 10 to the 14th, same order of magnitude. I'll just write it as per second. Okay? So the energy here, E, this is E for red, this is E for violet. I've got to sneeze. Excuse me. Y'all awake yet? Okay. Okay, sorry about that, Emmanuel. I mean, okay. All right. 6.63 times 10 to the negative 34 joule seconds multiplied by 7.30 times 10 to the 14th per seconds. This hertz. This per second cancels out the per second. And this is going to be something on the order of, that looks like 42.3, something like that. 4.84. 4.84 times 10 to the minus 19 again, joules. Okay, another good energy unit. So what is this? It's a lot more energetic, not a huge amount, but from 3.05 to 4.84, that's about 25% more, or maybe even 33% more. A good bit more energy. No lab to test.
No lab to test. What time do you think?
The test will be at 7:15. All right. So that is significantly higher. Now, guess what, folks? The red is down there close to infrared, which is heat energy, which doesn't come directly from the sun. It comes from degraded energy from the sun. Whereas the violet is up there close to ultraviolet, which causes skin cancers, cataracts, aging, wrinkles, that kind of stuff. That's beyond violet. That's why it's higher energy. Okay? It does damage to you. Thankfully, our atmosphere screens out most of the harmful radiation. Some of the ultraviolet comes through, and here is Lakeisha. All right. Well, I wonder who's that was talking with. Does anyone know?
Is that what the infrared lights?
What's that?
The infrared lights are 90 nano-ohm. You can't see with the eye with your.
Oh, yeah, right. And that's why in infrared scopes and glasses and things like this actually modify it so you can see it. And therefore, that's called night vision glasses. You can see heat moving around that you wouldn't normally see. Okay? And that's what law enforcement and other people use that to spies, stuff like this, to try to track people at night.
Wild animals.
Oh, yeah, animals, yeah. Hunters, I guess. Illegally, maybe? No, okay. Use it. Okay. Never that. Okay. All right. That was, okay. Let's clear this off the screen. Any questions on how to use Planck's law? Okay. Clear those off. So the atomic spectra. Now, they have this old name called black body radiation, okay? Everything gives off heat. If it's alive, if it's moving or operating or something, lots of things give off heat. It's a continuous radiation distribution. If someone were to put one of those scopes on me, they'd see different places have different heat, stuff like that. It's a continuous radiation distribution. It depends on the temperature of the radiating object. Okay, my temperature is sitting around 98.6, I guess. So I would be giving off a certain spectrum of radiation. Okay? Now, that radiation is also a characteristic of the specific solid, liquid, or some of the denser gases. So therefore, what the astronomers do when they look at some of these specialized telescopes out there at some of the far out stars, they can, if these telescopes are set up to measure the radiation distribution, they can determine generally about how much of that is hydrogen, how much is helium, how much is carbon, because everything gives out a different spectrum. Okay? So that's why it's characteristic of all solids, all liquids, and a lot of the denser gases. The less dense gases get sort of fuzzy and you can't really tell much there. Now, this is what I was just getting at. If you have a specific element there, its emission is at characteristic frequencies. Okay? Now, this is basically what Isaac Newton did. He took white light, probably used sunlight, and sort of defined it through a slit. I don't know if he did this, I think he did. And it's shown it into a prism. The prism, because the glass has different optical characteristics, they're called index of refraction, it refracts the red light more than it refracts the violet light. And this interface, it does it one way, when the other way, it then expands it again. And you'll see, if that was sunlight, you get red, orange, yellow, green, blue, indigo, whatever that is, and violet. They left off indigo because you really can't tell indigo. The reason they put it in there is so you can spell Roy, G, this is Boof, and it would be Biv if you put indigo in there. which is a color, but it's hard to distinguish. That is the natural spectrum that comes from the sun, the natural light spectrum. That's a diffuse spectrum. One runs into the other, into the other, into the other. Okay? Now, if you had just a single source of material there, you could get something like this. Now this looks like a fluorescent tube. I'm guessing that's something even more specialized than that. And let's say we send a narrow band up here, then certain light frequencies get split up, and this is what we call a line spectrum. It's an emission characteristic of characteristic frequencies, and this identifies a specific, and they call it an incandescent gas. So it has some orange, some blue, some violet. I don't know what that last color is supposed to be. Nothing much beyond violet. Okay? Then you would get what they call a line spectrum, as opposed to a continuous distribution. Okay? Boo hiss. Okay. The picture in your book has a lot more, a narrower line spectrum than this does. Okay? Light from an incandescent gas produces a line spectrum as atoms emit certain frequencies that are characteristic of each element. Can anyone think of a tube that has just a certain type of gas in it? These fluorescent tubes, it's not important what the gas is. Neon lights. And guess what's in neon lights? What gas? Neon! Okay, very good. Neon produces a certain spectrum. Okay? And because neon is a single element, and all of neon is going to produce a very special thing. Okay? Now, what are some of these tubes that emit certain very defined frequencies? We have a name for them. Yeah. Say again? Okay, not fluorescent. That's what these are. What I'm thinking of, lasers. Those are very narrow, well-defined lines, okay? So you have red lasers or green lasers or something because of whatever the gas is that's in there. Actually, laser stands for, well, I can't remember all what it is, but you've narrowed down, the frequencies are all building on themselves. So if you ever have a laser light, don't shine it in anyone's eye. It's such high energy, you can burn the retina. Don't do it, okay? Don't shine it. Oh, what is the? You can go blind, okay, or lose vision, okay. So these characteristic frequencies, when you have a single or a very limited number of gases in there, incandescent gases. The illustration here is for hydrogen is the Balmer series. There's another name. Goodness gracious, how many names are we going to run into in just one chapter? Okay. Who is Balmer? What's this series? I'm trying to find, oh, there it is. This is on page 212, the first column. They have a little blurb about that, but they say very little about it. I think that's what was supposed to be here. Okay? And it moves right into Bohr's theory. But let's go back to this and do example 8.3. Now this is based on the Balmer series. And here's equation 8.2 that they didn't even put down here. But here's the equation that Balmer came up with. Swift mathematics teacher, J.J. Balmer, we had a J.J. Thompson, now a J.J. Balmer. That must have been two lucky initials. Okay? 1 over lambda. Does anyone know what lambda stands for? Say again? No. It's just a symbol. It's a Greek letter lambda. Guess what it stands for? What is it similar to in the English alphabet? Lambda. L. Okay? And what does L, if you saw something that was L by W by length, L stands for length. What length is this talking about? Wavelength. The wavelength. So 1 over lambda, which is the wavelength of your spectrum, is R. Oh, what's that R? Okay. Come on, where is that R? I know, but they should tell you what that R stands for. Oh, they just say is a constant. Now, those with the big books, you can go back to your front inside cover and see if you can find what that R is. What did it say? 1.097 times 10 to the 7th. I sure don't see it here, do you? Yeah. Okay. There are a couple of different R's. I'm trying to think which one this is. I think this is called the Rayleigh constant. R-A-Y-L-E-I-G-H. I'm not certain about this. No, I'm sorry. This one may be the universal gas constant. They use R for a lot of things. I think this is universal gas constant, but they would have had it here, wouldn't they? I don't see it. They may not talk about it in this book. Okay. Anyway, it's a constant of nature. So it's R times 1 over 2 squared minus 1 over n squared. Okay? Well, what is that n? The n means you've excited this somehow, maybe ions going through the tube or something like this, and then when it passed, it jumped it up a level. N is how many levels it jumped up. Starting at level 2, jumping up to level n, okay? Then this would be the wavelength when it falls back down again. So, when n is equal to 3, this will be 1.097 times 10, ooh, that's an ugly 9, isn't it? Times 10 to the 7th, and I think that is per meter. It's 1 over meter. I think that's what that stands for, okay? Multiplied by, yeah, it would have to be 1 over meter. Multiplied by 1 over 2 squared minus 1 over 3 squared, okay? 1 over 2 squared is 1 over 4 minus 1 over 3 squared is 1 over 9, and this would be, least common denominator there is 36, so this would be 936 minus 436, which would be 536. Multiply that by 1.097 times 10 to the 7th per meter. See, this has no units because n doesn't have a unit. And what would that give you? Someone with a calculator. 1.097 EE or EXP7 times 5 divided by 36. Okay, 1.097 EE or EXP7 times 5 divided by 36. What's that? The R. The R there in that equation.
1.52.
Okay, right. Okay, then what you do then is hit a 1 over x key or a reciprocal key, exactly. And what do you get? 6.6 times 10 to the minus 7. Okay, well, you got 606. What was your number? Say again?
9, -9.
Okay, but what is the number
Oh,
before that?
656. I know.
Yeah, move the decimal 2 and you get -7. So you're set up in engineering mode. This is in just scientific mode, okay? And you see that's exactly what they got. And you could do it for the different ones. Well, that frequency, by the way, is the frequency for red. If you turn back to the previous problem, remember red light, they say 4 points. No, that wasn't. No, this is wavelength. This is metered wavelength. It's not frequency, sorry. Wavelength. And that is red wavelength. Okay. If you go up higher numbers, then the difference here is even smaller. Okay. This would be 1/4. And then when you go up to level 6, that would be -1/36. Well, that's going to be a very small number. And that very small number is going to be multiplied by that. That gives you a smaller number here, which gives you a higher lower wavelength. So you the lower the wavelength, the higher the energy, because the higher the frequency. We haven't gotten there yet, but that's where it's heading. Yes.
That's what I missed. You should say parentheses open, then 1.097 times 10 e to the 7, parentheses closed, parentheses open, 5/32 times reciprocal. That's
Yeah.
what,
Then you do reciprocal at the end. Okay. So that's how they came up with these lambdas. Now the figure in your book shows this, the visible Balmer series, and this is for hydrogen, has 2 violet lines. That's the n = 6 and n = 5. They're pretty close together. Then the blue-green line for n = 4 and the red line for n = 3. Okay? A pretty bright red line. So, based on that, let's see what we can do on example 8.3. 8.3. Calculate the wavelength of the violet line n = 6. We just about had it. 1/λ is equal to 1.097 times 10 to the 7th per meter. Okay. We got a mass exodus here. Times 1/2 squared minus 1/6 squared. Okay? So 1/λ is equal to 1.097 times 10 to the 7th per meter times 1/4 minus 1/36. Boo. Well, 4 will go into 36 9 times. So this will be 9/36 minus 1/36. Right? That gives you 8/36. A bigger number. Okay? So this will give you 1.097. I did copy that right, yeah. Times 10 to the 7th per meter. Multiply that by 8/36. Well, 8/36 will reduce to be 4/18. That would reduce to be 2/9. Okay? So, okay? Okay. So try this. Anyone with a calculator? 1.097. Anyone got one? Nobody has a calculator. Okay, she's going to steal his. Good. Okay. 1.097. You know how to do EE or EXP? Okay, it may be the arrow key, but let's see. EE or EXP, you got it? 7 times 2 divided by 9.
You said something. I didn't see. There's nobody in the room over there, but I didn't see a projector in there either.
Right, well, I've got the projector in the back.
Lady sitting outside the class here. She asked if it was Thursday. I think they might be having class.
Okay. So we might need to move back there. I knew those guys were going to leave by 5. So let's take a 5-minute break, and I'll get transferred down that way. Can we finish this first?
Yeah.
Okay. Okay. I'll watch you do it. You got 1.097.
1.097.
Can you see that?
I turned it
Oh,
off.
there it is. Okay.
Okay,
Okay, now
1.097.
you look for the EE key.
EE.
Okay. And then you type in 7.
7.
That puts the 7 here. Times 2 divided by 9. Divided by 9 equal. Okay, now reciprocate, which is, wait, let me find it. It's the
To the
1.
X.
Huh? No.
E to the X.
No. It's the 1 over X key. There it is.
Okay.
Press that key, and you get 0.00. Well, that's 4.1 times 10 to the 1, 2, 3, 4, 5, 6, minus 7. So it's 4.1 times 10 to the minus 7 meters. Okay? They got 4.11. His calculator didn't show enough digits. Times 10 to the minus 7 meters. All right, we'll stop there, pause there, and then we'll pick up again with Bohr's theory. We won't bore you with that, though. All right. We're in Chapter 8, along about page 212, Bohr's theory. This is not a boring theory, it's Bohr's theory. Okay? Now, if we haven't had enough names tonight, here's another one. Niels Bohr. Okay? Now, I'm pretty sure he was sort of Norwegian or Swedish. I don't remember which. Niels Bohr. He came out with this theory. Again, a quantum theory with 3 rules. This is how we overcame that dichotomy we had. The atoms can't exist, but we know they do exist. Okay, remember? Because in order to have a circular path, you have to accelerate. If you accelerate, you're radiating. If you're radiating, you're losing energy. If you're losing energy, you're dropping in the thing and you spiral down and crash. They didn't crash, so something must be wrong. Here's Bohr's theory. Electrons only exist in certain allowed orbits. It's the only place they can do. Within an orbit, the electron does not radiate. Even though it's a curved path, they're fine as long as they're at that one energy level, that thing. Now, radiation is emitted or absorbed when it changes a unit. And this is what I was talking about in the fluorescent tubes, right? When the energy goes by, the electron absorbs that energy and jumps up to a higher orbit. In the Balmer series, it went from level 2 to 3 for the red, to 4 for the blue, or to 5 or 6 for the violet spectrum, okay? Now, once it's up there, if the energy passes and it can't sustain itself there, then it drops down in orbit. If it drops down in orbit, it gives off a photon of that specific frequency, similar to what Balmer said, very similar type pattern there, and that photon is given off. Now, sometimes that's not light. It could be other electromagnetic radiation. It could be ultraviolet. It could be infrared. It could be any other type. In the tubes there, it's white light, or pretty close to white light. Okay? Kind of makes sense? That's Bohr's theory. Came out with this about 1913. Okay? And it built on Balmer, what Balmer had discovered. Now, these 3 little blurbs here are filled out, fleshed out a lot better in the book. So read the book. Always read the book. Okay. Now that leads to this quantum theory of the atom. The lowest energy state is called the ground state. The lowest level you can have. Okay? Now, if you remember back when we were talking about absolute zero, remember in temperature, we said that's as cold as anything can go. Now, when that was first hypothesized back around Kelvin's time, William Thomson's time, they didn't have this quantized theory. They had that at that level, all motion stops. So nothing is giving off anymore. You can't get any colder than that. Now that quantum mechanics is in play, all that tells you that's your minimum energy level. Never does all motion stop, but that's the minimum motion you can have. That's the lowest level that electron can go. Now, as it goes up, then it's increasing. Now, the Balmer series started at level 2, and it jumped up to 3 and fell down, or 4 and fell down, or 5 and fell down, or 6 and fell down. When it fell down from 3, it gave you the red light. When it fell down from 4 to 2, it gave you the blue-green light. When it fell down from either 5 or 6, you were both of those in the violet region. Okay? Now, the lowest energy down here at 1 is called the ground state. The higher energy states are the excited states. Like y'all are all excited to be here, right? Yes. Okay. All right. Now, the photon energy equals the difference in the state energies. When it goes from here to there, that gives you blue-green energy. Okay? Blue-green light. The hydrogen atom was the example. The energy levels were defined, and you came up with these line spectra that Balmer did. Matched them up with this, and here's your H frequency. That's the energy. That's the difference between the high energy and low energy. Now, in the old days, they thought the low energy was 0. It's never 0. It's just the minimum state, the lowest energy you can have. Okay? Now, what's a little confusing here is that the energies are given negative numbers. So this is a negative 10 to the minus 18. This one's a negative 5 times 10 to the minus 19. It's a weird way of doing it. And your electron energy, minus 13. Well, minus 13 is more negative than minus 3. It's more negative than minus 1. Yeah. So, yeah, this is a lower energy, but the number's bigger because it's a negative number. So it's a little weird how they do the numbering there, the energies. Okay? Now, this was Bohr's model. It worked on hydrogen really well. Based on the Balmer series, everything did well. The sad news was it didn't work on any of the other elements, okay? Because once you get more than one proton in that nucleus, you have charge distribution, you have all sorts of things that really screw up the model. As long as there's one proton here, everything else works pretty nicely. Okay? Bohr's theory only modeled the line spectrum for hydrogen. That didn't work for the others. Further experiments established this next phase, a wave-particle duality of light and matter. Boy, what in the world are they talking about here? Okay, here's what part of what it is. Originally, we thought energy followed in waves. The higher the frequency, the more energetic. The lower the frequency, the longer the wavelength, the less energetic. Okay, that was the first model. Then came these photons, which acted more like particles. Okay? So they did Bohr's model based on sort of that kind of concept or mixture. Well, as it turns out, light and any radiation, especially high energy radiation, has some characteristics of particles and some characteristics of waves. Here's another name for you, Young. Okay, I don't know if they give his full name here. And by the way, I forgot to mention it, in the book they tell you about electron volts. That's how you measure very, very small amounts of energy. Notice these all have exponents in the negative 20s, and negative 19s, negative 18. Those are extremely small numbers. And you have these a lot of exponentials in it. To make it a little easier, they talk about electron volts. A joule, if you remember right, is a, let me step back one. potential difference. Does anyone remember what the unit for potential difference is? Volt, yeah. But does anyone remember what a volt is? Energy per charge, joule per coulomb. So if you multiply the number of coulombs by the number, saying that wrong. The voltage by the number of coulombs, you get joules. Volts times coulombs equal joules. Well, a coulomb is a macroscopic amount of charge. On the microscopic, here you have electrons moving up and down. So if you have electron times a volt, they don't give it a new unit, they just call it electron volt. That's a charge times a potential difference. That's an energy unit. An electron volt is an energy unit. And that gets numbers that we can deal with. No exponents, no anything else, just numbers we can deal with. Okay? And that's what your book tells you. Bottom of page 213. That right-hand column. Okay? Okay, now we're going to the top of 214. Okay? Okay. There's a lot of stuff here that the book's not doing the slide set is really skipping over and glossing over way too much. Oh, and here's that picture we had earlier. These fluorescent lights emit light as electrons of mercury atoms, remember we called it a mercury vapor in there, inside the tubes gain energy from the electric current created by our big capacitors up there. As soon as they can, the electrons drop back to the lower energy orbits, emitting photons of ultraviolet frequencies. Ultraviolet radiation strikes the fluorescent chemical coating inside the tube, stimulating emission of visible light. So if you didn't have that coating in there, then those tubes are emitting ultraviolet light. Not that safe. In fact, there was a professor in the agronomy department at University of Georgia when I was there. He was kind of a weird old guy, nice guy, really nice guy, but had his idiosyncrasies. If he was in a room with fluorescent lighting, he wore a pith helmet. You know, one of those like the hunters use in Africa. Yeah. He wore it to protect himself from that ultraviolet light that may be getting past that white coating. He was a little strange. He lived with his mother and he was a nice guy. Later, I found out that when we moved to Birmingham, found out we knew his granddaughter, that was strange too. Small world. Okay. Here is equation 8.3. Okay? This is from Bohr's model. Okay? I need someplace to write it. Yeah, here it is. It's sort of already in here. E to the n is equal to e to the 1. That's this right here, negative 13.6 over n squared. This is equation 8.3. Yeah, 8.3 in your text, where they call it E1. This is E1. This is E2, E3, E4, E5, E6. Okay. That's the equation there. Okay. The second equation, 8.4, that's this one down here. This is equation 8.4. Okay. That H nu, that's the energy given off, okay, is equal to the change of energy levels between that. That was Balmer's formula too, basically. Not quite. That's Planck's formula, but okay. Sort of combines the two. Okay. Now let's do example 8.4. It's going to use those two. And I can't write it there. Where am I going to write it? There it is. This is where I'll write it. See if there's any other place. Let me see. Let me go back here. Okay, let's clear this screen. Okay. Example 8.4. An electron in a hydrogen atom jumps from the excited energy level N equal 4 to n equal 2. Okay? Jumps from n equal 4 to n equal 2. What is the frequency of the emitted photon? Well, from equation 8.4, you see that HF is equal to EH minus EL. Okay? Now the high energy here, EH, that is that's E4 here. E4 minus E2. And that's equal to HF. But you see, we're looking for F, so what we do is divide by H. Okay, if you turn back to the figure that you had before, well, I'll do it this way. Wait, wrong way. This one, E4 is negative 0.850. So over here, we'll do F is equal to negative, was it 0.850? 0.850 minus, what was our E2? Negative 3.40. A negative 3.40 divided by H, Planck's constant. And you'll have to turn back a page or two to get that one. .63 times 10 to the minus 34. 6.63 times 10 to the minus 34. Okay? Now that has a unit. That was joule second. Okay. The trouble is these other numbers are in electron volts. That's a problem. So we really need to write those in joule seconds as well. So let's go back. Sorry about this. No, I was going the wrong way. In joules, that was negative 1.36 times 10 to the minus 19. I was trying to avoid that. Okay, let me erase these two. Okay, and go back and write what they are. Okay. Negative 1.36 times 10 to the minus 19. Negative 1.36 times 10 to the minus 19 minus E2 was negative 5.44 times 10 to the minus 19. Where is it? Okay, negative 5.44 times 10 to the minus 19. 5.44 times 10 to the minus 19. Now we've got the right units because these were in joules and you're dividing by joule seconds. The joules will cancel, the differences in joules, the joules will cancel out and that gives you per second and that's a good number for frequency. So if you got your calculators, okay, negative 1.36 EE or EXP minus 19. Now, let me see your calculator before you do that. No, you don't have, that's a subtraction key. Here is the one that changes sign. You have to enter the number first and then change sign. I did. Oh, you did it. Okay, you're a smart dude. Okay? All right, you already got it handled. Okay? Subtraction key, a negative 5.44 times 10 to the minus 19, EE minus 19. Then equal divided by 6.63 EE or EXP negative 34. And what do you get? .63 EE 10 to the minus, or EE negative 34. I can't see what page we're on. This is 8.4. Oh, you shouldn't get a minus. No, you shouldn't get a minus. Okay, go back. Let's start again. The 1.36, change signs. EE 19 change signs, right? Okay. Then your subtraction key. Then 5.44 change sign, EE, 19 change sign, equal, that should be a plus number, shouldn't it? Okay, it's a positive number. Divided by 6.63 EE, 34 change sign, equal 6.15 EE times 10 to the 14th hertz. That's per seconds or hertz, because the joules go out and you get hertz or per seconds. Now 6.15, let's turn back to that figure again, and you see that's in the blue-green range. They call it 6.2. That's a blue-green, and that sure is what they got when they went from level 4 to level 2. Very good. All right. All right, we're ready to hit 8.3, which is quantum mechanics. So y'all let me know when it gets close to 7:15. Because we want to stop there, and we'll have our test on chapter 6. It's what? 6:15. We've got an hour. Oh. Okay. I can always check up on you. Okay.
Yeah, she just thought about setting a watch back. He did that back when I told her.
Yeah. Okay. Let's get into quantum mechanics. Okay. Quantum mechanics work on quantums, right? No, that's a different thing. Okay. The Bohr theory only. Okay, we already did this. Oh, here's where we left off. Further experiments establishes wave-particle duality of light and matter. And this is where we have here, okay? They mention Young here, and I cannot see Young in the book. Has anyone seen where this is? And by the way, if you read the book, you'll see we skip over a lot. A German physicist named A. Sommerfeld, okay? And, so there's lots and lots of things here. Yeah. So you'll just have to look him up if you want to write on him. I can't think of his first name. But anyway, he has a modulus named after him, Young's modulus. I just can't find it. Okay. Now, but what he did, he set up this two-slit experiment that produced interference patterns for both photons and electrons. The difference is the width of the slits. For electrons, I can't remember which way, they were either wider or narrower, but you can show that photons of light, which are wave nature, and electrons, which are particles, really, really small particles, they both show wave characteristics, they both show particle characteristics. Even a photon which has no mass still acts like a particle in some senses, okay? And the interference patterns, mostly that was a wave issue, but it also was another. So let's look at what they call matter waves. And here's another name, Louis de Broglie, okay? Now, a French physicist, okay? Louis de Broglie. Now, the reason I say it that way, when I took quantum mechanics as an undergraduate, I had a junior and senior level. Unfortunately, I had this guy from Ireland, right from Ireland. He had the strongest Irish brogue I've ever heard spoken. And he was talking about quantum mechanics, which doesn't make any sense when spoken in English, and I could not understand half of what he said. I wrote like crazy. Literally, that guy He was in a classroom that was like this, narrow this way, but wide this way, and it had 4 big panels of chalkboards on it. And he had a book in the bookstore that he said was going to be the text. I bought the book, and I went to class. He never, ever referenced the book. And everything he did in class, I could find maybe 1 out of 4 things anywhere in the book, and they were always in different chapters, nothing in any order. He was writing his own book is what he was doing, but he had to order a book for it, so he just picked one, and it made no sense. So he literally was working from his notes, and he was talking to the board the whole time, writing furiously, and we'd fill this panel, this panel, this panel, and that panel, and then go back and start again, erase this like crazy. Usually didn't erase too well, so it's hard to read, and did this panel and this. He usually got through 8 panels and started on somewhere on his next trip through in 50 minutes every day. And I couldn't understand half of what he talked to the board in an Irish road. And so I remember de Broglie, okay? He had the Broglie in there, okay? But Louis de Broglie, okay, in 1923 postulated that matter does have waves. Or that matter waves at you. I don't know which one. Okay. Wavelength is related to the momentum. We talked about momentum before. The wavelength of matter is related to the momentum. The matter waves in atoms are standing waves. Okay? This is sort of an interesting concept. Here is de Broglie's formula. Yeah, this is de Broglie's formula. Basically what he came up with. I don't know if it's called that. I think of it that way. The particle wavelength, lambda, remember that stood for a length, lambda, Greek letter lambda, is equal to h, that's good old Planck's constant there. It shows up everywhere. 6.63 times 10 to the negative 34 joule seconds divided by the momentum, mv. That's the mass. Now, when you're talking about this, that's talking about the momentum of a pickup truck. The mass times its velocity. You're not going to measure a wavelength with that. Okay? We're talking about electrons or very small things. I mean, that does, but it's not going to be measurable. This is measurable. Mass times velocity. So this will be kilogram meter per second. This is a joule. Boy, we're going to have to break down our units here, aren't we? A joule is a kilogram meter squared per second squared. Remember, that's a joule. Times a second, that's from here, divided by a kilogram meter per second. What does this? Kilograms go out. One of these seconds go out. That second goes out. And that meter goes out. And you're left with meter. That's what wavelength is measured in. Okay? Now, this is going to be a tiny number. This is going to be generally a pretty reasonably sized number. But when you're dividing by it, that makes that even tinier. So your wavelength is, pretty small. Okay. Actually, it's really pretty large compared to wavelength of energy. So that's your particle wavelength. De Broglie came up with that. Now, here's what we mean by a standing electron wave. Remember I said that electrons kind of orbit the nucleus, right? So you picture them just going around the nucleus. But they don't just go around in nice circular orbits, not even elliptical orbits. They go around in orbits that go in and out and in and out and in and out and in and out, and this is a standing wave. And as long as the electron is in that standing wave, it's got a fixed energy. Okay? And here's Amika. All right. All right, we're still missing Parker, and Wayne. What's that? Okay. What do you do? Go home and eat?
His phone right there.
It's still out there? It's out there? Oh, at the pub right now. Okay, I see. He's not eating. He's having a liquid lunch. Okay. All right. Now you see, if you tried to set up this as a orbit, that's not going to be a standing wave, that's going to collapse, okay? If these things don't match up, it's not going to work. And that was de Broglie's contribution. That matter waves, okay, because it sets up quantized standing waves that on average have that energy. Sometimes it might have more or less or whatever, but on average it has that energy. That is de Broglie. Another potential paper topic. Wow. De Broglie. Louis de Broglie. Okay? It doesn't sound very French to me. Louis does, but de Broglie, I don't know. Sounds like something else. All right. Let's do example 8.5. Let's see if we can find room for that. Here we have room. We'll erase this. Okay? And we'll do 8.5 here. What is the wavelength? So we're looking for the wavelength. Don't know what that is. Associated with a 0.150 kilogram baseball, okay, with a velocity of, so what's this, 0.150 kilograms? What's that measure? Come on now, all term long. What does kilogram measure? No. Mass. There's a difference in mass and weight, okay? Okay. With a velocity of 50 meters per second. They just told you what that was. That's the velocity. So what was the formula we just had? The lambda, I had it at the bottom of the page. I erased it. Lambda is equal to h, which was Planck's constant, 6.63 times 10 to the negative 34 joule second. Now I'm going to go back and rewrite that as a kilogram meter squared per second squared times second. So one of those seconds is going to go out. Okay? Going to divide that by the mass, 0.15 kilograms. You could have the extra zero if you wanted to. The kilograms are going to go out. Times velocity, which is 50.0 meters per second. Now one of the meters go out and the last second goes out. So multiply the numbers. Our unit is going to be in second. What is that? 6.063 EE or EE 34 minus. You punching it? Okay. 6.63 EE 34 plus minus divided by, first we'll do 0.15 and then divide again by, all right. Wayne is here. Okay. Divided by 50. Oh wait, did you do 0.15? 0.15 and then divide again by 50. 50. And what do you get? 8.84 times 10 to the minus 35 meters, which is your wavelength. That is an incredibly small wavelength. No wonder we're not going to see it, okay? The wavelength of light was 10 to the minus 14 or minus 7, something like that. This is so incredibly small, you're never going to measure that. Okay? Now, that's 8.84 times 10 to the minus 35 meters. What is the wavelength associated with an electron with a velocity of this one? So, second question, the wavelength associated with an electron. This was a baseball. Okay? Now we're going to do an electron. Okay? An electron. Well, we got to turn to the front of the book to get, and if you have the thin things, unfortunately you don't have it, the electron mass. Electron rest mass. And that physical constant's taught about the middle, lower part of the middle. See it? 9.11 times 10 to the minus 31 kilograms. Okay, you see electron rest mass? Okay. It's under Coulomb law constant, above proton rest mass, electron rest mass. Okay, under physical constants. Okay, about halfway down the list. Okay, electron rest mass. Okay, 9.11 times 10 to the tiny, tiny number, negative 31 kilograms, as opposed to baseball, 0.15 kilograms. That's a big difference there. Okay, and it said with a velocity of, so this is mass of the electron, the velocity of the electron is going to be 6 times 10 to the 6th, 6.00 times 10 to the 6th meters per second. That's a whole lot faster than a baseball. Okay? So we find its lambda, same way, 6.63 times 10 to the minus 34 kilogram meter squared per second squared. That's your joule times second. So one of those seconds goes out. And then your denominator is the mass is 9.11 times 10 to the negative 31 kilograms. Kilograms go out. Times 6.00 times 10 to the 6th meter per second. Okay? And then one of the meters goes out and the per second goes out. So we're left with meters. So if you have your calculator, punch away. 6.63 EE 34 plus minus. Okay, divided by 9.11 EE 31 plus minus. Divide again by 6, okay, just 6, EE6 equal. Okay, 1.21 times 10 to the minus what? 10 meters. Okay? Now look at the difference in that number. It's a small number, but it ain't nowhere as close as small as that one. This is 10 to the minus 35. This is 10 to the minus 10. That has another 25 zeros before you get to the first digit. That is a tiny, tiny number. This, you're back at the sort of in the range, not quite of light, but at least you're close to it. Light is about 10 to the minus 7. So you're within ballpark of that. All right. So you see, electron can have a measurable wavelength. A baseball, not quite. Not even a curveball. Okay. Okay. So if you sent an electron through, that's approximately the dimension distances between atoms in a crystal. So a beam of electrons through a crystal could produce diffraction. They've probably shown that. Okay. So that's matter waves. We've already hit this. Now let's get to wave mechanics. We had quantum mechanics, now we have wave mechanics, which is part of quantum mechanics, by the way. Tells me this is not quite right. If I had it all set up. Just these to drift. Okay. Now, wave mechanics were developed. Here's another name. Goodness gracious. In this chapter, we've had probably 5 times as many names as we had in all the rest of them added together. Erwin Schrödinger. Good Irish name, isn't it? A German name. Erwin Schrödinger. What wave mechanics does is treats atoms as if they're 3-dimensional systems of waves. before we showed the electron as a two-dimensional wave. Now you got three-dimensional systems of waves. Now the whole atom is a three-dimensional system of waves. Contains successful ideas of the Bohr model. Remember, it only worked for hydrogen, and a whole lot more. So it does describe hydrogen atom and many electron atoms, meaning more than one. Hydrogen only had one electron, so it was easy to model. Everything beyond that has many more electrons. And this forms our fundamental understanding of chemistry, wave mechanics. Okay? Developed by Schrodinger, who most people think of as a physicist, and yet it forms the basics for understanding how chemistry works. Guess what? Chemistry and physics are so intertwined, you can't really separate them. Okay? So, by the way, Schrodinger has a wave equation that is just unbelievable. Partial differentials, it's a mess. It's an ugly, ugly mess. And when I was having my orals for my, to pass the, I believe it, yeah. The math guy who was on my committee asked me to do something with the wave equation. And immediately I panicked, and my blood pressure probably spiked. I said, "You mean Schrodinger's wave equation?" He said, No. Just a simple wave equation, Oh, thank you so much. Okay. Schrodinger, it's a mess. Okay, so let's look at the quantum mechanics model. The quantum mechanics model assigns quantum numbers to specify the electronic quantum states. Okay? Every electron has a special quantum number, different from every other electron. And they specify these quantum states. Now, here's how they do it. The visualization. Let's first start with wave functions and probability distributions. Guess what? You can never locate an electron, even in a hydrogen atom. You can never say, there it is, okay. Because it's so tiny you can never see it. It has so little mass you can never measure it. It's going at a speed that you probably aren't going to be able to detect. So basically all we have is probability distribution. The greatest probability is somewhere fairly close to that nucleus, but it has a chance that it's somewhere way out there as well. So we're stuck, okay? And guess what? There's probably even some points way out here too. It could be. Not likely, but it could be. So what we do is narrow it down to get about 90% of the probability. We forget about these outliers out here. 90% chance it's going to be somewhere there. Okay? But the thing is, we don't know exactly where. It could be any one of those points, and even a few of these out here that are not there. Electrons are delocalized. Now, it's fun to think of them as following these standing waves, but where they are in the standing wave, we don't have a clue. Okay? It's there in there somewhere. Okay, I don't think this chapter is going to go into it, but actually another guy named Heisenberg came up with this principle, as if he thought things were complicated enough. You can never, ever precisely locate an object's position. If you do, you don't know it. There's no way you can know its velocity. Or if you precisely determine its velocity, you'll never know its position. It's called the Heisenberg uncertainty principle. There's just no way to know where it is and know how fast it's going at the same time, ever. Okay? These are in these microscopic things. So, let's get back to reality here, which is somewhat reality. The electron quantum numbers in atoms. We have 4 of them. The principal quantum number is N. That's the name it's given, the letter it's given. We call that the energy level. Think of N, energy, N. It's the average distance from the nucleus. We never know exactly where it is, but it's the average distance. Okay? Now, this is make a little more sense a little bit later. Let's just deal with it. The second number, principal quantum numbers N, the second one is called the angular momentum quantum number, and that's L. That's not an I, that's an L. It's not a 1, it's an L. That's a spatial distribution. Okay? Now, these quantum numbers N, they're 1, 2, 3, 4, 5, 6, 7. Okay? The angular momentum quantum number L, it's given letters. S, P, D, F, G, H. Now, we never go beyond H. Theoretically, you could, but we don't. Now, F, G, H sounds like it's going in alphabetical order. How they came up with this SPD, that's historical. But it starts with S, then P, then D, G, F, G, and H. In fact, I'm not ever sure I've gotten into G and H. I don't think I've ever gone beyond F. It's called the angular momentum quantum number. The third one, magnetic quantum number. That's the spatial orientation of the orbit. And they don't even give what its name. I believe it's M, but I'm not sure. And they don't even give the values here. We'll see that later. Don't worry about it. And the final one is the spin quantum number. That's the electron spin orientation. And there's several ways you can express it. You can express it spinning up or spinning down. That's one way. They usually say plus 1/2 or minus 1/2. There's several ways you can do it. That's the spin quantum number, sometimes called S, but you don't want to use S because you have one of the angular momentum levels is S, so we usually just call it spin. Okay? Magnetic and spin. We just give those names without really giving a symbol to it. Okay? Now, on energy level 1, you only have one angular momentum, and that's S. Period. In N equal 2, you have an S and a P. Now, the S is always, the 90% probability is going to be right around the nucleus. Somewhere in there. Almost spherical. Okay? Remember, this is 3-dimensional, not 2-dimensional. The P orbital, on the other hand, angular momentum L, the P level, forms one of these barbell type shape along one of the axes, primary axes. This one is along the X, you could have it along the Y, you could have it along the Z. Okay? Now, I'm going to jump a little bit ahead now. In the S level, you can only have 2 electrons. Only have 2. No matter what energy level are, in the quantum number L, S, you only have 2. One spin up and one spin down. That's it, okay? In the P orbital, you could have 2, 4, 6. One along each axis. 2, 4, 6. Okay? That's your P. So you can have up to 6 electrons. You may not have 6. You're going to have 1, 2, 3, 4, 5, or 6. Okay? Now, I'm jumping ahead. Here are the other 2 P orbitals. I said this one, they call them the Z. That's the Z. This is the Y. There's the X. They rearrange them, just like I said before, along each axis. You can have up to 2 electrons in each of those, so 2, 4, 6 in the P orbitals. Okay? We'll get to this later. I'm just giving it to you now. Okay? That's the, and by the way, at energy level 2, you can have S and P electrons, but no more. Okay? We'll get to that later too. All right. Here is the spin. They sort of skipped over magnetic, but here's the spin. Like I said, spin up or spin down. That's the only 2 options. Sometimes they say this is plus 1/2 and minus 1/2. Doesn't matter what you call it. Spin up, spin down is good enough. Okay? And that's why every time you can have 2 electrons, one can be up and one can be down. They go in pairs like that if they can. All right. Now this is table, okay. stop just a moment here. Oh, and in the book, they did mention the Heisenberg uncertainty principle. That's on page 217. Read that. You'll probably get a better understanding than my quick definition or description. Okay? But here's on 217, Science and Society. 2 types of scientific research, basic and applied. Okay? A lot of these dudes we were talking about, they were doing basic research. I mean, they were coming up with models and stuff that no one had comprehended before. Then you have others that's applying what the basic researchers had. For instance, fluorescent lights were applied research from the jumping of quantum levels, okay? Without understanding that that could happen, no one would have thought of doing this. There's not one more important than the other, but the pure scientists say the basic really is really, really important. Unfortunately, today, okay, the U.S. has a system of scientific research that has put us way ahead of the rest of the world. We have one of the best systems ever developed for doing this. The government helps, the states help, everybody contributes, private industry and stuff like this. When you get bean counters running that, though, they want applied research. They want something that they're going to see returns from. They do not really give a lot of emphasis on basic research that may not have any direct monetary value immediately. Sometime in the future, you might be able to capitalize on it big time, but sometimes it's generations between the discovery of basic research and application of basic research. So we are really hurting ourselves when we don't fund basic research. I'll get off the soapbox for now. Okay. Now, yeah, okay. You know what I was thinking. Okay. Now, here's what I was just emphasizing before. When you're in quantum level 1, your principal quantum level, n equal 1, you have only one L value, angular momentum quantum number, and that's S. It's not really a number, it's a letter. What's the maximum number of electrons you can put in there? 2. The S level only has 2 electrons in it. Now, if you will, turn to your periodic table, and suddenly this is going to hopefully make a lot of sense. N equal 1 is your period 1. It only has 2 electrons. That's hydrogen, and go all the way across to helium. Hydrogen has 1 electron. Helium has 2 electrons. It fills the S level of N equal 1. No other elements in that first row. That's why there's only 2 there. Because your first level can only have 2 electrons. Okay? Now, and by the way, hydrogen's very reactive. Every acid has hydrogen in it. Every base has hydrogen in it. All organic matter has hydrogen in it. Hydrogen combines with lots and lots and lots of stuff. Water is H2O, okay? Ammonia is NH3. I mean, lots of things have hydrogen. Very reactive. Helium, nothing reacts with helium. Nothing. It sits by itself. And that's why blimps are filled with helium, not hydrogen. Hydrogen's lighter than helium, but guess what hydrogen will do? Catch on fire, explode, burn like crazy. Helium won't. So the Goodyear blimp, helium, folks, not hydrogen. Okay. Then go to the second level, N equal 2. The first 2 elements, okay, wait. N equal 2 has 2 angular momentum levels. We call them energy sublevels, S and P. S can have 2, P can have 6. Look at your periodic table. Second row, N equal 2. Anyone looking?
Yes.
N equal 2, lithium, beryllium, they fill up S1 and 2. Then jump across the boron, count how many you got? 6.
6.
So boron, carbon, they start filling the P levels. 1, 2, 3, 4, 5, 6. When you get to neon on the at number 10, it's at the 8th one in level 2. There were 2 in level 1. 8 there, it has a full outer shell. It won't react with anything. That's why neon is also non-reactive. They call that last column helium, neon, argon, krypton, xenon, radon, the noble gases. They don't combine with anything else. No chemical compounds have helium or neon or argon or krypton or radon or xenon in them. They're individual. That's why they're gases. Radon is a really heavy atom, but it's not going to be a solid. It's going to float around as a gas. You don't want to breathe it because certain radon is going to radioactively decay. And if you breathe it in and it happens to decay while you got it in your lungs, it can cause damage. And if you had enough of it, it could cause lung cancer. Second leading cause of lung cancer after smoking. Smoking far outweighs it all, but after that is radon gas exposure. Radon is a naturally occurring element in the soil. Fortunately, where we live, there's not a lot of it. But up in Huntsville and some of the limestone areas, there's a bit more. Okay, still not dangerous. All right. When you get to, is it 7:15? No, it can't be. Okay, when we get to N equal 3, the third energy level, here you can have an S with 2, a P with 4, and a D can have up to 10. Now they draw in the book the D orbitals. There you see the P orbitals. The S orbitals are spherical. 2 electrons anywhere in the sphere. The P orbitals, 1 along each axis. Okay? The D orbital's a mess. There are 5 different orientations they can have. And it's really hard to pick them out there. A 3-dimensional structure, each of 5 sets of lobes that hold 2 electrons each. So 5 sets of lobe, 2 electrons, that gives you 10 electrons in the D orbitals. Okay. Now here's where things start getting a little messy on our periodic table. Because you see when N is equal to 3, you get sodium and magnesium, they fill the 2 S electrons. Then you go to the P's, you go across the aluminum through argon. That's your next 6. But you don't see your D10s. And the reason is, even though this is energy level 3, the S sublevel and P sublevel and D sublevel, at N equal 4, S is lower energy than 3D. So actually you fill these 2 first. So that's why you go down and fill 4, 1, and 2 before you do it. And you count how many are across there in the transition elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are your D10. They're actually 3 D10, but they come after 4S2. Okay? All right. Then you jump up to 4P6. Those are the next over there. Gallium through krypton. Okay? And then you would think you hit the 4D10. You don't do that until you fill 5S2. So they don't show it when you get 5S2. So this is what's happening in each of the main energy levels and the sub-levels. But they don't line up this way. This is the lowest, next, 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 then next, 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 next. I mean, it jumps around on you some. Because some of the sub-energy levels of higher are less than the higher sub-energy levels of the lower. It's kind of a mess. We'll see how to straighten it out in just a short time. I don't know if we'll get to it tonight or not. Okay? What you say? Okay. Next slide is electron configuration. This is 8.4. Okay? All right. 8.4, electron configuration. What we're doing with this is naming, in some senses, kind of locating, but not really. You're describing the arrangements of the electron into the atomic orbitals. And that's what I was just trying to introduce you to in the last slide. Remember the principal quantum number, that's your N. The angular momentum quantum number, that's your L. Then we have the magnetic quantum numbers. They specify an orbital, okay? I haven't said that. And then altogether, they specify the atom's quantum state. Now, they didn't mention here the spin quantum number, but that's in there too. Now, have we had enough names for the night? No, here's another one. Pauli, another Italian, I think. Let me see if I can find them. Pauli. I can't think of his first name, and they don't list him here. Oh, here we go. Wolfgang. So he wasn't Italian. He was Austrian. But you know, these people moved across borders so much, that name sounds Italian, but he was really Austrian. Wolfgang, now that sounds German or Austrian. Wolfgang Pauli, an Australian physicist, he summarized what we've got here, okay? The Pauli exclusion principle. Here's what he's saying. Each electron has a unique quantum numbers. N, L, and then the angular and spin. Maximum of 2 electrons per orbital. Maximum of 2 electrons per orbital. I already told you that. The 2 electrons, one has spin up, one has spin down. That's how they can have a unique quantum number. The chemical properties are determined by that electronic structure. If you remember the last slide, the last entry a few slides ago, well, I'll get to it. Right here, the wave mechanics forms our fundamental understanding of chemistry. This is how it does it, through these quantum numbers. Chemical properties are determined by this electronic structure. What will interact with what else in what manner? How do they combine? What kind of crystals do they form? What kind of angles do they make? All of it is defined by this electron configuration. So how do we write this? Okay? The electrons fill orbitals in order of increasing energy. Not by increasing numbers always, by increasing energy. And I've already told you this, and here it is again. The shell capacities, S, only one shell, 2 electrons. Because every energy level can have only 2 electrons. How do you distinguish? One spin up and one spin down. That's what gives you a unique number. The P, remember there are 3 different orientations. Each one has 2 electrons, so 6 electrons can go there. The D, I can't describe, is 5 orientations somehow there, each one containing 2, and therefore up to 10 electrons. Okay? And then the F, and like I said, we never really go beyond F. Theoretically, you could do G and H, but we don't. There are 7 possible things there, 2 electrons each, 14. Okay? Now, we'll come to this in a second, but let me go back to the periodic table and point something out to you. And here's why it's true. Okay, I've already said the S is represented by the 2 here, or L, the first one, hydrogen and helium. After that, the first 2 are the S. Then the P's, which are 6, count them off. 1, 2, 3, 4, 5, 6. And then the D10, count them off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, where's L14? Come down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's where it is. So you see the 2s are your S electrons, the 6 are your P electrons, the 10 are your D electrons, and the 14 down here. You see the 14 go in here. But if you did that, it would be so long you couldn't get it on the page. So they pull that down and put it down there. So that's where these numbers fit in the periodic table. Okay, so let's pick strontium. 38 electrons. How do we know that? Find strontium in your periodic table. I'm guessing it's number 38. Sure enough, there it is, strontium, number 38. What does that 38 stand for? How many? No, protons. The atomic number is how many protons. But if it's a neutral atom, it's also the number of electrons. So you're right too. It is number of electrons. So strontium has 38 electrons. Now, we've got something to help us here. I'd never seen this before I found this book. I know it's been around otherwise. Here's how we fill these. Okay? Okay, is everybody looking? We start here and do the 1s electron. So that's 2. So strontium, we'll start the process. Strontium, what was it, SR? You remember what its symbol was? ST?
No.
SR, that's what I thought. Looks like senior, okay? Okay, strontium. It has 38. The first 2 are in 1s, so we put 1s2. Okay? That's 2. We got 36 more to go. Okay, now where do we go from there? We go around and get back on here, follow the arrow, and then we do 2s. So it's 2s2. That's 4 electrons. We got 34 more to go, right? So we go from here, back around here, and then we do our 2p. 2p, and p can hold how many? 6. Okay, so now we're up to 10 electrons. We got 28 to go. Then we go to 3s. 3s, how many can s hold?
2.
2. S hold, I didn't say, never mind. Okay. So, hey. Just because you're standing. Okay, never mind. Okay. That was 12. So we have 26 left to go. Okay? So after 3s, we go back around here and we do 3p. How many will p hold? 6. So that gets us up to 10, 18. So we have 20 left to go, right? Okay. After 3p, we do 4s. 4s, how many will s hold? 2. So you see, folks, what we've just done, we've done 4s before we did 3d. Even though this is a higher energy level, the sub-level was higher energy here than the energy level 4. So 4s2, and now we circle around and go to, now they actually do this number. They do it inside. And maybe that's neater. I like to go on the outside. It doesn't matter. Okay? So what's next after 4s? 3d. Okay? And how many will d hold?
10.
D holds 10. Okay, now what are we up to now? There's 10, 20, 30. We're up to 38 to go. Right? And what's next?
2.
4p. 4p. See? 3d, then 4p. 4p, how many will 6? Yeah, p holds 6. So we have 2 to go, and guess where they are? 5s2. There is strontium. Where did you find strontium? In the level 5, number 2, 5s2. 38. There it is. You see how we got it? Okay. Now I'm going to erase my chicken scratch here, and we'll see how they did it. All right. There they've listed it. They just threw it all up there. But what you do, you follow this down there. I'll show you how they usually do in the book. They do it like this. To me, it gets sort of confusing, like that, and like that, and like this. If you like it that way better, mine was getting a little messy. And then like this, and then we ended up here. But this is the order you fill them in. Did you see this? Do you understand it? Guess what's going to be on the lab?
Right. This.
What?
This. Yes, you should have been paying attention. Okay,
It's gonna be on the
I
lab.
got it.
Parker's here, I guess.
It's gonna be on the web.
Okay. Okay, I think we've got everybody here who's coming.
Time for the test,
Not yet.
please.
No, wait. What I want to do is go through my spiel again. Okay? This is going to explain how we're going to do the rest of the term. Today, when we reach 7:15, how long is that away?
15 minutes.
Hey,
15 minutes.
okay. Did I give you the other things? Okay. Okay, can you wait a few minutes? Because they're right in the middle. You can sit down if you want to. Okay. Okay. All right. What time did you say it was?
I'm doing this for you manual now.
7:05.
7:05. We got 10 minutes before we start the test. So let me explain the rest of the term. We'll continue this for 10 more minutes. Then we'll have the test on chapter 6.
7. It's 7. 7.
Okay? We'll have the test on chapter 6. Okay? We can. Okay? Now. Okay? Excuse me. Okay? We'll have the test.
Right.
When you finish the test, you can leave. Most of you will finish before the 30 minutes, but I'll be here afterwards. So you can take as long as you need. I hope you got your formula and equation sheets for chapter 6. Okay? Now, that's today. On Tuesday, we'll pick up wherever we leave off here. And guess what? We only have, I think it's 2 more sections to go here. So we'll easily finish that on Tuesday, I think. Okay? And since we're going to easily finish it on Tuesday, here's the spiel, folks. I asked the class if you'd like to have pizza one day, and they decided, before y'all got here, to have it Tuesday rather than Thursday. Okay? Pizza. And I thought we'd have it late, but they said, no, let's have it early. So we'll have pizza Tuesday at 3:15. Do any of you have dietary issues that I have to order anything special on the pizza? Huh? Okay, yeah, if y'all want to arrange drinks, you can do that. So what I've had requests for, and the people who got here early got to put in the request. 1 Supreme, 1 Meat Lover, 1 pepperoni, and I figured we might ought to have a cheese if anyone can't eat meats. Okay, I'll get up to 1 more pizza. I can double up on one of those, or if you have another favorite. What?
Cheese.
Say again?
Cheese.
Okay, 2 cheeses?
No, just one.
1 cheese.
Yeah.
Okay? He's wanting to cut the cheese, okay?
Another pepperoni?
Another pepperoni?
Did you say cut the cheese?
No, I didn't. I would never have said that. Okay. No, okay. All right.
What is cut the cheese?
Never mind. Hey. Y'all are getting out of control. Okay. So what we'll do then is have pizza 3:15 on Tuesday. And if y'all, I said y'all could buy your own drink, bring your own drinks, non-alcoholic drinks, and we will have pizza on Tuesday. You'll probably be late getting here, right? We can save you a little bit. Okay. Now.
What you talking about?
Okay. Next. Okay. Next.
Next.
We'll finish chapter 8, and as soon as we finish chapter 8, we'll have the lab on chapter 8. And part of the lab is what we were just talking about, folks. Too bad you weren't listening. But it's on Screencast-O-Matic, so you can go pick it up. Okay, now, after you finish the lab, if you want to, you can go home. Okay? But anytime after we finish the lab on Tuesday, anytime you want to, you can take your Chapter 8 test. It's going to be a lot like the other tests, mostly multiple choice. A few fill in the blanks, maybe a couple calculations, I don't remember. But anyway, won't take you more than 30 minutes, I don't think. Okay? Anytime after you finish your test, Chapter 8 test, you can do the final exam. That's 20 or so questions, matching. Not multiple choice, matching. I think everybody will finish probably within 15 minutes, but you got hours.
The final exam is on all the chapters?
All 6 chapters.
All 6 chapters.
Okay. The 2 or 3 major concepts in each chapter. Come up with about 20 questions. Okay. Words and their definitions, that type matching. Okay. So, what I'm saying is, if you finish your lab on Tuesday and you want to leave, you certainly can. But you can come back anytime, Wednesday or Thursday, and do either 1 test or 2 tests. As long as by the end of Thursday, 8 o'clock Thursday night, everybody has done both of the tests. Remember, you can't drop the final. No matter what average you have going in, you cannot drop the final. So, if you want to take both tests even as early as Tuesday, after we finish the lab, you can. Or you can go home, study, and come back Wednesday and take one or
What
both.
time Wednesday?
Anytime. I'm here from 7:45 in the morning until probably 4 or 5 in the afternoon. And then on Thursday, 7:45 in the morning until 8 at night. Lots of time. You pick your time anytime you want to take it. I'll be here Tuesday and Thursday till 8. Yeah. I can't hear you.
So if you're happy with all your other test grades, can you just skip the last test and drop it and go straight to your final?
That's up to you. You do get to drop your lowest test score.
Oh, I didn't hear what Wayne said.
He said, if you're happy with your other test scores, can you skip Chapter 8 and do just the final? You can, but you have a good chance of making a better grade in 8. And frankly, I'm not saying you, but frankly, a lot of people have missed a lot of labs, and you're not going to have a very good lab average at the end. You might need all the points you can get on your test average. Okay? Say again? Okay, well, I need to get them. And by the way, here's the other thing about the spiel. Tuesday is the last day of class, so therefore all your research papers are due in by Tuesday. I'll take them tonight. I'll take them tomorrow. I'll be on the Birmingham campus. You can slide them under my door here if you want to. I'll take them Monday or I'll take them Tuesday. After Tuesday, you start losing points. Okay? And Tuesday at the beginning of class on Tuesday, I'm going to be returning everything that you've turned in except the research papers. When I say that, it's all labs and all tests. So if you haven't finished a lab or a test by Tuesday at pizza time, 3:15, it's going to be too late. So get everything into me, all labs, all tests, by 3:15 on Tuesday. Now, I won't be able to return those to you until I get them graded, but when I get them graded, I'll return them to you then. Okay. Any questions? That was my spiel, how we're going to end the term. Really, when you take your test, it's up to you. I'll be here all night Tuesday, all night Thursday, as normal. Or you can come in anytime from the finish of lab until 8 o'clock Thursday night. Yes. For the what?
Lindsay, that's your lab.
Oh, the bonus points? No, bonus points in tonight. Tuesday, you just get your score. But after Tuesday, you start losing points. Okay. Okay, if you turn it in? Okay. Yeah. Okay. You know, I'll be on Birmingham campus tomorrow. You understand? Okay. All right. Yeah. Okay. If you turn it on Tuesday, you get no bonus points. If you turn it on after Tuesday, I mean Wednesday, you're losing points. Okay? I'll still give you credit, but you'll be losing points. Huh? Say again? 7:45 to 11:45 in the morning only. Okay, you can come and slide it under my door here. When I come in, no, my office door, 265. When I come in Monday morning, I'll count that it got there before I got there. So, okay, you can do that too. But remember, they don't like it. Okay. Any other questions?
No.
Okay. All right. There's another concept applied in the book: fireworks configuration. Firework configuration. Certain strontium, atomic number 38, we just did, chemicals are used to add the pure red color to flares and fireworks. It is 7:15. I was just pointing this out. There may be a potential paper topic. How do they get the colors in fireworks? One way, the red comes from strontium. Probably never heard of strontium before, but you've appreciated a red flare that they use for emergencies. Strontium is in there. That's what does it. All right. So, do y'all want a little break before you start? Okay. All right. I'm going to end the screencast-o-matic if there are no more questions.